So this is Arduino for total newbies. I just started the recording, even though I missed the intro to myself and the Arduino, intro to Arduino, but the rest will be here. So that's the more important stuff anyways. Yeah, so we're not going to solder together this board. I'll just have them ready-made. And if you have an Arduino board, get it ready and I'll show you how to use it. And even if you don't have an Arduino board, don't worry about it. I'll show you the information and you can do this anytime. Okay, and the slides will be available afterwards. So are there any questions on what an Arduino is and why they're cool? You can type them in the public chat. I'll look at that. And if you have questions anywhere along the way, don't wait for a slide with questions written on it. You can type a question anytime. And sometimes I'll get carried away and I won't see a question maybe. And if Serge, who's a volunteer coordinator, a facilitator rather, for this workshop, if you see that there's a question waiting and I'm not answering it, maybe you can just butt in with your voice.
Will do.
Thank you. No questions are coming up, so I'll move on. Let's learn about electronics. Electronics is not just for white men in lab coats or old white men in lab coats. I can be an old white man in a lab coat, and if you live long enough, maybe you can too if you're white. But you can be any color and buy your own lab coat, and you don't need to be a specialist or anything. Anyone can learn about electronics and play with it and learn. I'll give you a simplified model for how this all works. Electronics is named after electrons. It's all about electrons with electronics. Electrons, there's this fancy model with a nucleus in the middle of an atom with these electrons flying around the outside doing crazy stuff. And if you really want to learn about it, then you get in more and more into quantum. And according to quantum, electrons don't even exist. What the hell? So we're not going to learn about quantum today, but quantum is totally cool. I encourage all of you to learn about it. But in our model of electronics, simplified model, there are atoms, and there's these teeny little things called electrons, and they have minus charge, and the middle with a nucleus has plus charge. But moving these little teeny things, they can go from atom to atom into atom in a wire and move them around, and that's what it's all about, pushing electrons around. Electrons kind of love being pushed around, as it turned out, and if you push them around in a circle, then they can do cool things. And that's what electronics is all about. And check this out. See these electrons? These are electrons being pushed around in a circle. And look, they're all smiling. And you know why? Because electrons love being pushed around in a circle so they can do cool things with electronics. And that's what we do. These obstacles, those are we're not bullies. We are not bullies. We're only bullies if we're doing it non-consensually. Electrons love being pushed around. And if we're doing it consensually, everything is cool. So these obstacles are also consensual. They're there to do cool things when electrons jump around them and through them and over them and all sorts of things, right? So these are electronic parts. The obstacles are electronic parts, and when the electrons go through them or over them or around them, they give them some energy to do the cool things that they do. We're going to learn about most of the electronic parts that people use to do lots of cool things. And with the ones that I'm going to show you, you can do amazingly cool things, including turn TVs off in public places. So, and again, that's just an example. So, the way you get electrons to move around. Oh, one thing I wanted to say, let's go back to that. Electronics, you have to have a complete circle. I'll do it with my little red dot here. You need a complete circle for the electrons to go around and around and around and around. No breaks in that circle. And you've probably heard the word circuit before, lots of times, I'm sure. The technical definition of a circuit is a complete, unbroken circular path for electrons to flow around and around and around in. That's the technical definition of a circuit. And here's a circuit. It's kind of stylized, but Normally, you don't see the electrons smiling, but in this workshop, you do. That's one of the advantages of this workshop. So the way you get electrons to go around and around and around in a circuit, an unbroken path for them to flow around, is to push them. And you need to push them, and you push them with a power supply. And power supplies can take on lots of different forms. Here is an old power supply from a desktop. Here's one that's my laptop's power supply. We also have a big power supply, which is, this is the European one, which has 240 volts. That's a lot of volts to push electrons around in, and it's enough to kill you. We're not going to do that today. Hopefully none of you are going to die during this workshop. If you do, sorry. But what we're going to do is use batteries. Here's some AA batteries, and they can fit in a battery pack. Here's a battery pack. I got lots of battery packs. I got lots of batteries. That's what we see a picture of there. There's a couple wires coming out that we can connect to microcontrollers and other parts. And they have AA batteries in them. 3 of them. And with that, we can push electrons around, and they can have fun going around and around and around in a circle. The batteries are AA batteries. You've probably all seen them a lot. Yeah, cell phone be gone is very easy, but they are illegal. It's easy to buy one, though, online. I don't encourage anyone to break the law, but anyone can go online and find one. They're called cell phone blockers. But yeah, they are illegal. If they weren't, I would sell them and make them, and I'd sell millions of them. So anyways, batteries. Batteries are one really cool power supply. If you look right here, it says 1.5 V. 1.5 V is the amount of push a AA battery can give to electrons. And that's a lot of push. But here we've got 3 AA batteries. Each of them is 1.5 V. So that's 3 times, and I'll talk about that more in a bit. But V stands for victory. In my German class, it also stands for verbs, which I'm kind of obsessed with lately because of my classes. But here it stands for volts, and and that's named after Alexander Volta. Alexander Volta is a dead physicist. In electronics, we name everything after dead physicists. There are a lot of dead physicists. I'm going to go over a bunch of dead physicists today, actually just a few of them, the most important ones. And V for volts, named after Alexander Volta, is the first one. So that's the amount of push that electrons can give to electrons, volts. That's the push, Okay, so 1.5 volts in a AA battery. Here's a AA battery in our circuit now, being shown pushing the electrons around. Okay, so they go around and around and around and around and around and around and around until the chemistry in the battery dies and there's no more energy left. And then the electrons they're not as happy as they used to be, but you can always put a new battery in, or you can use another kind of power supply like solar energy that's renewable. So when you push electrons, depending on the obstacles that we have here, here's a couple of obstacles, electronic parts. Depending on these electronic parts, they slow the electrons down a certain amount. The volts in the battery pushes them to try to make them go as fast as possible with the amount of volts push they can give. The parts, though, are slowing them down. But the end result is they're going speed around and around and around and around. The speed is called current, measured in amps, named after André-Marie Ampère, a dead physicist. Okay, so amps, that's just the speed of the electrons. That's current. The speed of the electrons is current. Yeah, age has nothing to do with any of this. If you're just born and you're interested in electronics, you can play with this stuff. And I did, and I had a lot of fun doing that, and I hurt myself a lot, and I'm still alive to do it. The electrons are way older than we are. If you're into big bangs, they've been around that long. So yeah, so the speed of the electrons going around and around is current measured in amps. More amps, more speed. Okay, so next slide. Here's the exact same circuit, but with 3 times the push, 3 times the amount of volts. In the battery pack, there's 3 AA batteries. Each one's 1.5 volts. 3 1.5 volt batteries is 4.5 volts. Sorry for the math, but that's the math that we're going to do in this workshop. I hope you could handle it. No more math today. Sorry about that. So if we push the electrons 3 times harder, they go 3 times faster with the same obstacles, the same electronic parts, the same electrons going around and around. And that's 3 times the push with the batteries. That's 3 times the speed, 3 times the current, in other words, which is measured in amps. So there's 3 times the amount of amps. Make sense? Kind of simple. You now have almost all of the basics of electronics. There's one more thing though. The thing is, if you have electrons going around and around and around and around, they go through those electronic parts. Some of those parts, let's go back there. Some of those parts might be a little bit sensitive, and if they're going really fast through them, they might give that part a little bit too much energy, and then the part burns up. That is kind of sad, and we usually don't want to do that. Smoke goes away, and sometimes we even say the magic smoke has left the part. And once the magic smoke goes away from the part, we can't put it back in. So we usually don't want to let the magic smoke out. And in order to prevent that, there's an electronic part that exists only for making sure that we can slow down the electrons so that they don't have too much energy to burn up other parts. And this here is a happy person in a mud bath. That represents the electronic part that slows electrons down. If these electrons are cruising around, they're going really fast, but then this one here hits the mud bath, it slows down. And these electrons are actually really, really close to each other. They're like touching each other. It's like worse than a traffic jam in Los Angeles. So if this one slows down, all of them slow down the same amount with this one part here that slows electrons down. And these parts are called resistors. Resistors are the part that slow down electrons. That's their job. They slow down electrons. And resistors are measured in ohms. That's this word here, ohms. And that's named after Georg Ohm. He's a dead physicist, of course. We also know Georg for another thing, which is Ohm's law, which I'll get to in a second. Okay, so, oh yeah, back to here. Now you can see the relationship here. If we're pushing on electrons here with volts, they move. If we have parts in the way, like resistors, they slow down. So if we push on them, if we have more volts, they go faster, more current, more amps. If we put a part here with resistance in their path, they slow down. More ohms, more resistance, slows down, less current, less amps. More voltage, they go faster. That's more current, more amps. But if we have more resistance, that's more resistance, less speed, less current, less amps, right? That's the relationship. That is Ohm's law. I'll show you something before I say just a bit more about Ohm's law. This is the same circuit as the one before. It's just that the resistor, the happy person in a mud bath, is shifted over just a little bit to the left. But it doesn't matter. It's one resistor, and the traffic jam in LA of electrons, which are still happy, they don't even care if there's a traffic jam. They're still going the same speed. It doesn't matter where the resistor is. It can be anywhere in this circle, even more to the right, or even over there, upside down, to the right of the red wire, to the left of the black wire. It doesn't matter. We can put that resistor anywhere in our circle, in our circuit. It's the same circuit. electronically speaking. So Ohm's law is this relationship, which you now know. It took me 4.5 years of university to get to that, but you now know it in 40 minutes, less than 40 minutes. So volts is the force that pushes electrons. Amps is the speed of the electrons, and ohms is the resistance that slows them down, that puts resistance in their path. And Ohm, Georg, he was really clever. He figured out this relationship all on his own a long, long time ago, before we even had light bulbs and before we had batteries even. So he figured it out mathematically. Volts, using dead physicists that we know of today, volts equals amps times ohms. That's Ohm's law. We're not going to actually use that equation today, but I want you to know that. And yeah, no social distance. Electrons work whether there's a pandemic or not. So I want you to be aware of Ohm's law, because if you play with electronics enough, you will want to play with this simple equation. But you can also figure out what resistors to use, what batteries to use, or what other power supplies to use by tinkering. You know, if you get it wrong, it won't work. And it's possible that the parts might lose their magic smoke. But fortunately, parts are cheap. Some parts aren't so cheap, but there's usually like a quarter of a cent. A resistor is a quarter cent, and batteries are cheap, and all these other parts are cheap. You can always order more, and they come from China. They come halfway around the world, which is a bummer, but they're cheap. It takes like a week though, so you usually don't want to let the magic smoke out, but you can tinker, and if anything breaks, you just order more parts. But with Ohm's law, if you do it right, then you don't have to worry about burning parts out. There's one thing I also want to say, and I'll say this a few times. Electrical engineers, which are the people in the white coats and all that stuff, they are really insecure. They're insecure. So they want job security. So they do all these things. They have all these different names for the same thing, and they confuse other people. And so, but don't worry about that. I'm going to show you a bunch of different things that they do to try to confuse other people. Don't be confused by that. But the Ohm's law for electrical engineers is not V equals A times R. It's E equals I times R. Electromotive force equals, that's the old word for dead physicists used, equals I times, and then they use a fancy symbol, which is the Greek letter omega, which I'll show you next. And I can't remember now what I stands for, darn. I'll have to look that up again. Anyways, you can look it up. But E equals I times R is the way they do it in the fancy electrical engineering terms. But it's just volts equals amps times ohm, and it's just the relationship which you know without the equation. Inductance and capacitance I'll talk about just a very little bit later. So let's not talk about them yet. So here's the symbol for ohms. It's the Greek letter omega, which is the Greek letter for O, omega, the last letter of the Greek alphabet. And here's a funny comic that I saw online, so I thought I'd share it with you. Geek humor, whatever. So next slide. Here's what resistors actually look like. They can be really small or they can be really big. The big ones have, you can see here where it actually says 4 ohms right here printed on the big resistor. And I is not ideal. Oh, I see. I is not inductance. I is not ideal current source. It might be intensity. I can't remember. So, but here it says 4 ohms. On these smaller resistors, here it says 100 ohms on this one. On these smaller ones, they have colored bands to show you the color, the amount of resistance. And there's a color chart. When I was 6 years old, I memorized this, and so I can look at a resistor and without thinking tell you how many ohms it is. But you don't need to do that to play with electronics or resistors. You can ask the internet with your favorite browser. That's what the internet is for. And most projects nowadays, they'll give you the color code too. But if it's not there, you can always look it up online. So that's what resistors look like. Why would you want to? Again, to slow down electrons, it's really important to have this electron slow enough so that there's not so much energy that they burn out a sensitive part, because some parts can burn up with electrons going through them too fast when there's too much current, too many amps. Okay, and so that's the job of resistors. They slow down the electrons, they limit the current to a point where you can guarantee that it won't burn up any parts. And that's important if you're doing especially something with life support, but even if you're just doing blinky lights, you want your things to work and not to burn out. I'm not going to answer that question of exactly what goes on when magic smoke goes away, because that gets kind of complicated depending on the part, but we can talk about that later. You can ask me later. So before I show you some new parts, let's talk a little bit more about the two parts we already know, which are power supplies and resistors. So a power supply, if it's batteries, it has a plus and a minus side, because it matters how you hook it up. Like here's a power supply with two wires coming out, a black wire and a red wire. And you can see on the slide that there's two wires. Unfortunately, the black wire is hard to see here in the slide. It's easy to see on my slide presentation, but big blue button with a darker background, it's hard to see, sorry. But the black wire is minus and the red wire is plus. And if you hook it up backwards, do you know what happens? J-Red has the answer correctly. The magic smoke can go away. But even if the magic smoke doesn't go away, your circuit won't work, because the circuit is designed to have the electrons go in one direction and one direction only if it's one designed with batteries. If a circuit, if a part has polarity, that means that it matters how you hook it up. A battery pack or a AA battery all on its own, it matters how you hook it up. If you look at a AA battery, one side will say plus and the other side will be marked minus. It matters how you hook it up. So here it is again with this mark. The red wire is plus, the black wire is minus. But again, electrical engineers are very insecure, so they call them all sorts of different names for the same exact thing. So here's just all the different names that we can use. Power is also the red wire, plus and positive. We can also just call it by the amount of volts. And since there's 3 AA batteries in here, 4.5 volts. Often it's also called VCC, the CC voltage, and that's left over from really old days, the 1950s, 1960s in electronics, where there was vacuum tubes, or valves as they call them in the UK with actual English. And those are those old things that glowed kind of orange and got hot and were in lots of old electronics. We don't use them much anymore, but they're still cool for really high-end audiophile, because they are way better for distortion properties for audiophile audio equipment. But whatever, VCC, you have to know that word if you play with electronics. You'll see it again and again. For the black wire, it's called minus negative. It's also sometimes called 0 volts, but usually and almost always it's called ground. It's called ground, and you do need to know that one. You need to know ground. Ground is called that because way long ago, when the dead physicists were alive, they saw that that voltage was actually similar to height in many ways. So if a power supply, well, let me say, so you can't see me, but I'm in a chair and my feet, can you hear my feet stamping on the ground? My feet are on the ground, and the tabletop that my laptop is on is 1 meter off the ground. If I just say that my tabletop is 1 meter, what does that mean? It has to be 1 meter from somewhere, and it's 1 meter from the ground, the reference. And it's the same with our power supply. If I say that the red wire here is 4.5 volts, what does that mean? It means it's 4.5 volts from the black wire, the ground. Okay, so 4.5 volts from ground. So we always need a reference with our voltage. And just to answer your question about the size, of the physical size of the battery, the bigger it is, the more chemistry it has, the more chemicals it has. So it takes longer for the chemicals to wear out. So it can last longer. But the physical size does not matter as far as volts goes. Different kinds of batteries use different chemistry. So, and the chemistry determines the volts, the amount of push. There's no such thing as a wire that can hurt you more unless it's got a sharp point at the end. Then it can hurt you. It's the current that hurts you. If enough current goes from this finger to this finger, like I have a power supply between here, now I am part of the circuit. The electrons are still happy, but I won't be. If the voltage is small enough, it can only push the electrons so fast, and so it won't hurt me at all. Like here, this power supply, I can touch this. That's no problem. 4.5 volts, I won't even feel it. No one feels that. But if it's 120 volts coming out of the wall, or 240 coming out of the wall here in Berlin, I will die. And you would too if you did that. Not necessarily die, but you won't like it. And if you keep it there, then you will die. Usually you let go, which is a good thing because most people don't want to die if they're alive. Yeah, so please, as Konilov said, don't do that. There's no judgment on me. I won't try to stop anyone from doing anything that they actually do want to do, but I encourage you to look for other options first because there are so many options in the world. And it's worth trying more of them before you try that. So electronics is much more fun when you're alive. So I encourage you to stay alive and keep playing. It's current that can hurt you. The speed of the electrons going through your heart can make your heart stop. And keep your heart going, keep your brain going, keep your body going, keep your life going, and do cool things. That's what it's all about. And that's why I'm sharing what I'm doing, so that more people can play and have fun and share with other people and keep making things cooler. So yeah, unfortunately, the Big Blue Button messed up these two pictures here. These used to be pictures of resistors with colored bands. This one, they're upside down from each other. But you can see the happy person in a mud bath, which is the representation of a resistor. It doesn't matter if a resistor is right side up or upside down. They slow down electrons exactly the same either way. Resistors do not have polarity. It doesn't matter which way you hook a resistor up to your circuit. Okay? On your tongue, 4.5 volts you might not feel, 9 volts you definitely feel on your tongue. And that's a way a lot of people still test out one of those little square 9-volt batteries to see if it's dead or not. If the chemistry is still very strong in the battery and touches your tongue quickly, then it doesn't feel good, but it doesn't like damage you. But if the battery's dead, it just tastes kind of salty. So here's the next part. Yay, we're finally on to our third part. And I'll go through the next parts rather quickly now. So this part is polarized. It's called a diode. And let me answer this question first. What's considered dangerous is 30 milliamps. But it's kind of debatable, and there's not a specific standard. But 30 milliamps is enough to make your heart stop. But 30 milliamps, it's really, really, really difficult to die that way because most people will let go way before it hurts anything. Because it hurts. So the resistance of a human body from here to here is about 100,000 ohms. And one thing I didn't mention with resistors is electrical engineers are also lazy. So we have shortcuts for things. So ohms, there's 100,000 ohms, there's 1,000,000 ohms in all. We have a shortcut. So K for kilo, Greek letters again, Greek words again, K kilo thousand, just like kilobytes or kilobits, whatever. M for mega, million, megabytes, megabits, mega ohms. So body from here to here is about 100K ohms, 100,000 ohms. And if you have 5 volts, you can determine how many milliamps you have. And if you have 100 volts, yeah, and a milliamp, yeah, thank you, Daniel. A milliamp is another Greek thing meaning a thousandth, 1/1000th of an amp. And there's also micro, which is 1/1,000,000th. And we even have pico, which is a millionth of a millionth. And I'll show you that one as well. So let's get to our third part. This is called a diode. A diode is a part that allows electrons to go through only one way. They can go through one way, no problem at all. It's almost as if that's not there at all. But the other way, they can't go at all. Okay, so it matters how you hook a diode up because it allows electrons to go only one way. And there's a colored band. It doesn't matter what the color is. There's one band that shows you the minus side. Here, this one's black. This one's gray-white. That's the minus side. And the other side, of course, is plus. And we aren't using diodes today, but all of you have seen a special kind of diode. All of you have seen more than you can possibly count in your life because there's a special kind of diode called a light emitting diode. When electrons flow through a light emitting diode in the way that the electrons can flow, the current can flow only in one way. If the current's flowing in the way that it can flow through a light emitting diode, it emits light, which, by the way, is why it's called a light emitting diode. So in this case, the LED is emitting green light, light that we perceive of as green. The manufacturer that makes this diode designed it that way. We don't have control over the color. We only have control over how bright it is. An LED is a diode, so it does matter how you hook it up. There's a short wire and there's a long wire. The short wire is the minus. The long wire is the plus. When electrons are flowing in the way it can flow, it emits light, in this case, green light. And I wanted to say also, electrical engineers don't call these wires when they're on a part. Yeah, we're trying to confuse people. We call them leads. We call them leads because I guess they lead to the part. I don't know, but that's what we call them. When a part has wires, we don't call them wires, we call them leads. So LEDs all have a long and a short lead. The short lead is minus. And here we see a whole bunch of different colors: white, blue, green, different colored green, yellow, and orange, red. We can even, and they're designed by the manufacturer to be that way. They even make ones that emit light that we can't see. Our eyeballs don't respond to the color. So there's above violet, called ultraviolet, and people often call that a black light because it makes it look like it glows in the dark. And then there's also a color below red called infrared. In super high power, which you can't get from an LED, in super high power ultraviolet, that's what comes from the sun to give you sunburn. But ultraviolet LEDs, there's no way it can harm you. An infrared and super high power from the sun is what absorbs into your skin and makes the sun feel hot. But LEDs, again, they don't give enough infrared to harm you in any way whatsoever. But there's all these different colors. We can control the brightness of an LED by the amount of current that we put through it. So if the current is flowing just a little bit, it's going kind of slow, the LED is emitting only a little bit of green light here. But if we make the electrons go faster by pushing on them harder with more power from our power, so more volts from our power supply, or less resistance in the path, then it gets more current, faster electrons, more current, more amps. It's brighter and brighter and brighter until the magic smoke goes away. And then the LED will never light up again. Fortunately, LEDs only cost a couple of cents or even cheaper, or if you have super fancy ones, sometimes a little more, but they're cheap, so we can order more. But usually we don't want them to burn up. So that's why we use resistors. So here's a resistor in line with an LED, and we almost always have a resistor in line with an LED so that the magic smoke is guaranteed to never go away. And we can, if you want to, use Ohm's law to determine the value of this resistor, or you can just use a solderless breadboard and plug in different values in to get the brightness you want, and hopefully it doesn't burn up. And if it does, hopefully you have more LEDs and more resistors. So yeah, and by the way, it doesn't matter which side the resistor is on. Just like that happy person in the mud bath where it didn't matter where it was in the circle. But of course, to make an LED light up, we need a power supply. There's no power supply here. That LED is not lit up. But before I show you how to do that, I just want to tell you a couple more words because, again, electrical engineers are really insecure folks. So we didn't never say things are in line with each other with electronic circuits. That's called in series. So if you play with electronics, you'll hear that word. Two or more things in line with each other are called in series. Two or more parts across one another, that's called in parallel. So if you play with electronics, you'll hear those words. Let me load the next set of slides, number 2. Big blue button is limited to the number of the size of your slides. So let's change that. That worked. Oops, we've got the wrong one there. That's the end. Go to beginning. Okay, so let's make this LED light up. Right now it's not lit up. It's ready to be lit up. We've got the LED with the long and the short lead. And again, do you remember which one's minus? The short lead is minus. So don't worry about memorizing the stuff that I'm telling you. The stuff that's important, I'll repeat a bunch of times, and that's one of the ways we learn well. And you can go over this again and again and again. So we've got the LED with the long and the short lead, the minus short lead and the long plus lead. And we've got a resistor in series so that no magic smoke will go away after we hook the power supply and turn it on. So here is a power supply. And again, I'm sorry that you can't really see the black wire here. Here's a little black wire from the power supply. Here's the red wire. And do you remember which of these is minus and plus? Ground is minus, the black wire. Red plus, okay, or VCC. All right, so we've got to hook up the black wire and the red wire to here and here. Now we got a 50-50 chance that if we don't know what we're doing, we hook it up right, and we have a 50-50 chance that we'll hook it up wrong. But just, you know, think about it for a moment. So we want to have this one here, this short one minus ground, and this long one is plus. So what we want to do is have this red wire go here through a resistor so no magic smoke goes away. The long lead of the LED goes through a resistor so no magic smoke goes away to the red wire. Okay, and the short one, the ground, the minus of the LED, is going to go through a wire to the black wire of our power supply. Okay, and then check this out. The power supply has a switch, and it says on and off. Right now it's off. Before you hook a power supply up to your circuit, even a simple one, it's off. Because if you do something wrong, if it's off, there's no electrons being pushed around, so nothing bad's going to happen. And then after you hook everything up, then you can double check it if you want to. And if you're really geeky and anal like me, you can triple check it, or you can ask someone else to. And then you can turn it on and see what happens. And then magic smoke might go away anyways, because, you know, shit happens. But so Again, make sure it's off before you wire it up. But let's wire it up. Here's the plus wire from our power supply. Red plus is going to go through a resistor so no magic smoke goes away to the plus. Or it can go directly to here as long as the resistor is somewhere in there. It can be on the minus side. But in this case, it's on the plus side. So it goes to the resistor, to the plus side. And then the minus side here is going to get a wire to the ground of a power supply. Here's more words. So here's the wires hooked up, and just the red wires hooked up. And now here's the black wire. You can sort of see the black wire here. So it's hooked up. Let's turn this on and see what happens. Look, when you turn it on, now electrons start flowing. They flow out of here into the LED, and then through the resistor, which slows them down, and then through here, they get recycled in the battery chemistry and then pushed out again through the LED, through the resistor that keeps it slow, and through here, recycled through the chemistry, and around and around and around and around and around and around. And the LED has a bunch of energy that it's emitting in the form of photons that hit our eyeballs, which we perceive, in this case, as green light. And that's a circuit that makes an LED turn on. And then if we turn the switch off, then the electrons aren't flowing anymore and the LED's off. So there's a really, really simple circuit. And you can do that. Anyone can do that if you have the parts. But let's do that with this here. I've got one of these kind of batteries. This battery here is really small. It's called a coin cell. It's called a coin cell because it's the size of like a quarter or like a euro coin. Here's one in my hand, and I don't know if my camera can focus well enough. I don't know, but you can see right next to my finger is a plus sign. So this side of the battery is plus, and this side is minus. And it says on here, it's hard to read, but it says 3 volts. This is a 3-volt battery, just like 2 AA batteries, except this one is small, so it won't last as long. So here's an LED in my hand. It's got a long and a short lead. So I want to hook up the short lead here to the minus of the battery, and I'll hook up the plus lead here to the plus of the battery. Oh, and check that out. Whee, it's fun. Okay, and after a few seconds, it's boring, but you can make an LED light up this way. I just cheated, however. There's no resistor in series with either lead to guarantee no magic smoke goes away from the LED. Why? Well, it's because these batteries, coin cells, because of the chemistry that makes these work, when you manufacture them, there's built-in internal resistance. And I just happen to know that that internal resistance is enough to guarantee that no magic smoke goes away from the LED that I used. So, but let's say also, what happens if I hook up this the wrong way? So here it is hooked up the right way. I can hook it up, make it go on and off. I can give you Morse code, and but let's hook it up the wrong way. Here it is the wrong way. The plus is on the long lead, the plus is on the short lead, and the minus of the battery is on the long lead. It's backwards. It's not lighting up. That doesn't hurt the LED. No current flows because the LED is a diode, and the diode, its job is to make sure electrons only flow in one direction. So it's not, no electrons are flowing, no photons are coming out. It's not going on to the camera or our eyeballs. We're not seeing it. But then we turn it around to go the right way, and it works again. Some of electronics is very forgiving. Some is not. And if you play with it enough, you absolutely will find out which is which. It's part of learning. So yeah, so there's our first actual working circuit, virtual in this case, through the magic of 21st century technology. which has a lot of technology in it, including lots and lots and lots and lots of LEDs on our screens. So yeah, so here's again this exact same circuit that you saw before, picture form. But now instead of a green LED, we have an infrared LED. The infrared LED, when we turn the switch on, it's on now. It's, so the current's flowing, it's coming in here, it's going through here through the resistor, which keeps the electrons slow enough so it doesn't burn anything up through here, recycled through the battery chemistry and out and around, making photons come out and around and around and around and around. This is emitting lots of infrared photons. Our eyeballs don't respond to it, but it's really bright. Devices that can respond to infrared light will respond to it, such as the remote control receivers on televisions. That's how remote controls work on TVs. They actually work with infrared light that we cannot see, blinking on and off and on and off and on and off at just the right intervals, so that when the infrared receiver on the TV sees it, then it will respond and do the right thing and turn the TV off, and thereby making the world just a little bit better for everybody. So that's a good thing to do. To get, so every TV manufacturer, well, many different manufacturers use different codes, so the timing interval of on and off and on and off of infrared is different. Many manufacturers have different models, and many of the models are different. So it took me a year and a half to get all of those intervals of infrared going on, off, on, off, on, off, on, off. But of course, I made that open source, so no one has to do that again. But it did take me a year and a half. Fortunately, no one has to do that again. But I was obsessed with this, and the more I did, the more obsessed I got, and it was really fun to do that. And I got to do lots of field testing at Best Buy, like I said earlier, which is also fun. And many of the managers, by the way, at Best Buy, who I told about this, thought it was really fun, so it didn't hurt anybody. So anyways, if you could, you can't. It's not physically possible, either for this switch or for our fingers. But if you could physically do so and flip this switch on, off, on, off, on, off, on, off at just the right intervals, you could make an off code for, say, a Sony television or a Panasonic or a Philips, et cetera, et cetera. But the intervals are too small and you have to be very, very accurate. We can't do that physically, mechanically with this circuit. But a microcontroller can be programmed to make those intervals. And if we hook up these parts with a power supply to our microcontroller, and there's the correct program in there, it can make these parts, control these parts to make this infrared LED go on and off and on and off at just the right interval, so that it can make an off code for a Philips, it can make an off code for a Sony, it can make an off code for a Panasonic, a Toshiba, a Fujitsu, a Samsung, an LG, et cetera, et cetera, et cetera, et cetera, and turn off every TV that we come across in our life. And as we do that, of course, we make the world a better place, not only for ourselves, but for everybody. Really fun to do this. So that's what I'm going to show you in the coming slides. So yeah, on, off, whatever. We can control this LED, making it go on and off. I already went through that. Yeah, let me show you a TV Gone remote control, and there's another video here for that, the last video that I'll show. We, like I said, cannot see infrared, but the cheap video camera in my phone can, and that's what I recorded this video with. So TV Gone, when you push the button here, it starts emitting off codes from the little blip at the top. The red light going blipping shows you that an off code is coming out. every blip of the red light means an off code's coming out. And that flickering, you're seeing white there, that's the infrared light that the video camera on my phone sees. There are hundreds and hundreds and hundreds of codes, and you can see the red light still blipping. That was only a few seconds of it. Every one of those blips of the red LED was a new off code coming out, the infrared LED. And the infrared LED is here. You saw that blinking in the video camera. In actuality, you can't see it in life, but the TV does. And every time this flickers, if the TV is programmed to respond to that flicker, it will do the right thing and turn off and make the world a little bit better for everybody. So, but there's hundreds of codes, so it takes about a minute for all of those codes to be transmitted through the infrared light. And then the TV Be Gone goes into a low power mode, waiting for you, the user, to do it again, and then make the world a better place for everyone again. The range of a TV Be Gone, this version of TV Be Gone, is about 9 meters, maybe 10. Sony TVs are 10. Some TVs are more sensitive than others. Sony TVs, by the way, are the best. They're very sensitive and they turn off very well. So I recommend, if you're going to buy a TV, it should be a Sony TV so that it can turn off well. I have a TV Be Gone Pro, however, which has lots of infrared LEDs and a bigger battery, and it goes 100 meters, because you never know when you'll need a professional to turn TVs off. So that's how TV Be Gone works. It's actually quite conceptually simple. The hardest part was collecting all the codes, but I'll show you in the coming slides how easy it is. But first, just a couple more parts, a few more parts. This part comes in different shapes and sizes and colors. This is a capacitor. A capacitor is like a little bucket we can pour extra electrons in our little electron bucket when we don't need electrons now. And when we need electrons a little bit later, we can pour the little electron bucket out and use that extra energy. So for instance, when we're blinking an LED on and off and on and off, like turning TVs off and making the world a better place, when the LED is off, we don't need much energy. So we can save some energy from the battery by pouring a little bit of that energy into our electron buckets, the capacitors. And when the LED goes on, suddenly we need a bunch more energy, so we can empty the electron bucket out and help the LED blink brighter. And this helps our power supply be smoothed out so it doesn't have to do as much work and the battery lasts a little longer. And so that's one way we use capacitors. There are actually a bunch of other ways too, but I won't go over that. Capacitors have two major kinds, the small kind here and the bigger kind. And they come in different shapes and sizes. And but the small kind, it doesn't matter how you put them in a circuit. They're not polarized. They can go in the circuit and work exactly the same either way, going in this way or this way. The bigger ones, however, you can see they have a long and a short lead. Because of the chemistry process used in manufacturing, there is a plus and a minus side. And like LEDs, the short side is minus and the long lead is plus. Capacitors are measured by how big the electron bucket is. The more it can hold, the more electrons it can hold, the more energy it can store. It takes longer for it to fill up and longer for it to empty out. You're kind of like really small batteries in this way. And you can actually get something called a supercapacitor, which is really, really, really huge, which actually is used as a battery. The amount of capacity for storage, for charge, is measured in farads here. That's named after Michael Faraday. He's another dead physicist, of course. And Michael Faraday, he's dead, but we remember him and how much charge we can store in a capacitor, how much capacity a capacitor has. Okay, these little ones are either in microfarads or picofarads, micro millionths, picomillionths of millionths, 10 to the minus 12. These bigger ones are usually in microfarads, or really, really big ones, which are supercapacitors, can be as big as a farad or 2 or 3 or 10. Farad is a big unit. Okay. Flux capacitors are a totally different story and are outside of the scope of this workshop. Yeah, sorry. And switches. Switches are super simple parts, but they're really important. They're pieces of metal that either touch or don't touch. So check out my fingers here. If there are 2 pieces of metal, not fingers, but metal pieces, if I touch this piece of metal like this, then the 2 pieces of metal are touching and electrons can flow through them in either direction. But if there's a gap, okay, now the switch is off. There's no way for electrons to flow, unless it's really, really huge amount of volts, and then there can be a spark going, and that's a lot of volts that need to do that. But it's really cool to have things that do that if you're making a really old 1950s Hollywood movie, and that's always got to be in the background. But in electronic parts, switches, electrons don't jump across that, make a gap. Lightning, by the way, is exactly that. It's a lot of charge way up in the sky and ground, and the charge from here loves going to ground, and it connects, and you don't want that going through you. It's kind of a bummer. So, or so I'm told. And but a switch, off, on, off, on, and there's lots of different kinds of switches. So the kind of switch which I'll show you, which we'll actually use today, is a push button switch which has a spring. So when you push on it, it goes down. When you let go, the spring makes it pop back up again. There's also kinds of switches that slide. So slide on, slide off, slide on, slide off. And then there's the toggle ones, which you have to push down, and then again you have to push back up. Toggle switch. So you can see here just a few small switches. Those are easy. Okay, and here's the coolest part, back to microcontrollers. This is why we're here, microcontrollers. They make our life totally amazing and totally annoying if they're in a cell phone, but so it goes. And this microcontroller is the one we're going to use. They have names. If you look on here, this one says ATmega 328P. That's the name of the microcontroller used on the least expensive Arduino board. You can use these not in Arduino boards. They're using lots and lots of other things, but they're using Arduino as well, which is why we're using this one today. So ATmega 328P, it's not a very nice name, but it's a name. And yeah, so that's its name. And it can do lots and lots and lots of amazing things. This microcontroller runs up to 20 million times a second. 20 million times a second. And electrical engineers, being lazy as we are, we call that mega. M, big M for mega times per second. And I'll get back to that one in a bit. So it also has memory inside where we can store its program. It also has memory inside where we can temporarily store stuff. That's called RAM. Where it stored its program is in flash memory. That's kind of like its own little hard drive. And it has 16 megabytes, 16 megabytes of program memory. That's not gigabytes, it's megabytes, million bytes. And it has 2 kilobytes, 2 kilo, K, 1,000, 2,000 bytes of RAM. Not giga. Giga is 10 to the 12th. So yeah, like our modern computers. But these can do a lot with these pins going only at 16 million times a second, and not like 4 giga times per second, like modern computers. We can do a lot with 16 million times per second, these few parts, and just a couple of thousands of bytes of RAM. And it's really amazing what we can do with this stuff. But like All computers, no matter how much RAM, no matter how much big your hard drive is, no matter how fast or slow it's doing, all computers, all they do is run a program. That's all of them. I'll say it again. The only thing a computer does is run a program. When you turn it on, it's running a program. It'll keep running program until you turn it off. On your laptop, what it's doing is running the operating system eventually, and then the operating system can jump to another place where it runs an application. On a microcontroller, the program is controlling the parts connected to these pins. Okay, so if we connect power to this microcontroller, it's running a program. Whether we put a program in it or not, it's running a program. And we want to put a program in it, and I'll show you how to do that later. For now, we'll just assume that you can do that. But all of these pins have different functions, and in order to find out what those functions are, you need a data sheet, or someone who's already read the data sheet and put it in the project documentation. Data sheets are sometimes pretty complicated. Some data sheets are more complicated than others. The one for this, it's made by a company originally called Atmel. They got bought up by another company called Microchip, but they still use the Atmel brand. So Atmel data sheets are pretty good, but it's still not exactly exciting, action-packed bedtime reading. There's 250 pages in the data sheet for this. If you look online and look for ATmega 328P data sheet in your favorite browser, you'll get this 250-page document. And it shows this picture where I got the picture from and all its pins, and it shows you what each pin does. 2 of the pins are special purpose that are used for nothing else but power and ground, or VCC as they call it here, and ground. Pin 7 is power, pin 8 is ground. But in order to know which is pin 7 and 8, we have to know which is pin 1. And on all chips that are made, even teeny little ones and bigger ones like this, there's a black indented dot right here in one corner, which shows you pin 1. And then they count counterclockwise. So pin 1, pin 2, pin 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, 15 is over here, 16, up to 28. Okay. Many chips, not all, also have this half circle indented at the top of the chip. And pin 1 is always to the left of that, on the left side of the top of the chip, even though the picture here shows it at the bottom, but that's the top, that's considered the top of the chip. Okay. So if we hook up pins 7 and 8 to a power supply, such as this one, and turn the power supply on, it'll be running our program. And if we put a cool program in there, it will be running our cool program. So right now, this has power and ground hooked up correctly. Black ground from our power supplies hooked to the ground lead here, which in this case is pin 8, and the power lead red plus is hooked up to the power lead of the microcontroller, pin 7, and it's on. So it's running a program, but big deal. There's no parts connected to the pins to have the program do its cool thing and affect our world in a cool way. So we have to connect parts to the pins. And we have to know what those pins do. So there's all sorts of things that pins can do. Today I'm only going to talk about 2 of the functions, but they're the most important ones, and they're the things that are done almost all the times. And yes, thank you, Mark. The data sheet shows you what all these pins do. But all of these pins can be used for inputs and outputs. And I'm going to talk about output pins first because those are super easy to explain. And then once you know what output pins are, input pins are super easy to explain. All right. So output pins. Before I get to that, though, I just wanted to mention in passing that there's today with digital electronics. With digital electronics, there's only on and off. There's only power supply voltage. If we're using this power pack, 4.5 volts, and ground, 0 volts. Those are the only choices. With digital, we either have power supply voltage or not, on and off, etc. With analog electronics, we can have any voltage. We can have the power supply voltage, 4.5. We can have ground, 0 volts, or we can have anything in between. Anything, 1 volt, 2 volt, 3.7463342, any amount of voltage. So analog in many ways is kind of more complicated because of that. And I'm not talking about analog today. We're only talking about digital today, because computers are either on or off, which means power or not. And that means it's easy, kind of. Actually, it is easy. It's lots and lots and lots and lots of easy things put together in perhaps complex ways. But we can do a lot with this. So again, electrical engineers are insecure, so we call on and off lots of different things, but it's all the same. We can have power supply voltage or not, power and ground, high or low, on or off, 1 or 0. They're all exactly the same and all interchangeable, and people use all of them all the time. Usually, though, when people are talking about this stuff, it's either on or off, high or low. But it always means that there either is power or there isn't. Voltage or no, current or no. Okay, that's digital electronics. And an output pin can be either high or low, on or off. But how do we make a pin an output pin? Well, you tell it to be an output pin. You tell the microcontroller to make a pin an output pin with one instruction in our program. It can be the first instruction, it can be the 10,000th instruction, it can be any instruction, doesn't matter, but it's an instruction. And here I just chose, let's make pin 13 an output pin. So the instruction is, yo, microcontroller, hey, dude, make pin 13, your pin 13 an output pin. And then from then on, it's an output pin until you turn it off and on again, and then it resets. But you can also have another instruction later that says, yo, microcontroller, pin 13, make it an input pin. We usually don't do that, but there actually are a few times where you do that, but I won't talk about that today. But it's just an instruction. It says to make a pin an output pin, and you can use any of the pins. Once it's an output pin, you can then have another instruction making that pin high or low, on or off. If it's high, there's power supply voltage there. If it's low, there's ground there. And we make it go high or low with an instruction. So it's just, yo, microcontroller, pin 13, that output, that output pin, make it high. And now it's high. And it stays high until you have another instruction that says, yo, microcontroller, pin 13, make it low. And now it's low. We can make it go high and low just with more instructions. We can say, microcontroller, pin 13 high. We can wait a specific amount of time, or we don't even care how long. Or we can make it really short, really long, months, years. As long as we have power, it'll keep timing, and we can do that. And we can measure that time. We can make it on and off and on and off at any interval that we want, including on-off codes for TVs. But we can also blink LEDs slow enough so that human eyeballs and brains can see them. So that's what it's really all about. So how many people here are software geeks? Normally people raise their hands, but don't worry about that. A bunch of you out there I know are software geeks and want to learn a bit about a hardware. But even if you're not a software geek, don't worry about it. You don't need to know how to program at all in order to play with microcontrollers and Arduino especially. But software geeks all know that the first thing that you do when you install a new programming language on your laptop or your phone is to print the words "Hello World" on your screen. And if you can do that, then you know everything's set up well and you can do anything from there, right? So the equivalent of that for microcontrollers is to make an LED blink. If we can make an LED blink with our microcontroller, then we know everything's set up well, our development environment and all that stuff is set up, and then we can do everything. So that's what we're going to do. The equivalent of hello world in microcontrollers, we're going to make an LED blink. Hello Cure World, yeah. I'll give you energy for that. So let's make an LED blink without a microcontroller first, as we've already seen. So this is a review of seeing how a microcontroller, an LED can blink without a microcontroller. Okay, so here's our circuit. The LED is on because the red plus wire, power wire, is hooked through an LED, through a resistor. So no magic smoke goes away to the long wire, plus wire of our LED. And the short ground minus wire of the LED is hooked to a black wire, the minus wire, the ground wire of our power supply, and the power supply is on. So the electrons get pushed out from our power supply, the batteries get pushed in here, through here, the LED gets energy and emits the energy in the form of photons, in this case green photons, and through the resistor, so it's slowing it down so no magic smoke goes away, and through here recycled through the battery chemistry and pushed out again and around and around and around and around. We see lots of green photons, so it looks really bright green on our eyeballs, right? And if we turn this off, then there's no way for electrons to flow, so it's off. And that's the way we make an LED blink without a microcontroller, just with a power supply and a switch. With a microcontroller, we do exactly the same thing, except our power supply for the LED comes from an output pin instead of directly from the power supply. So let's take the power supply away. There's no power supply, so the LED is off now. We can put any power supply we want on here. We can have, instead of that big power supply, I can have this coin cell and put that between the black and the red wire, the ground and the plus, ground and power. As long as we hook up the power supply correctly and it allows the electrons to flow in the right way, the correct way, it'll light this LED up, which is a green LED, so we'll see green light. And then we can take it away or put a switch in series and make it go on and off and on and off. Or we can have a microcontroller output pin connected to the red wire, the power wire, because the microcontroller output pin is a power supply, but it's controlled by our program to be on and off as long or as short as we want. And then we've got this black wire here. What do we do with that black wire? Electrons need to have a complete circle for the electrons to flow. So we always have to have the black wire connected to our ground, the reference, which is the black wire of our power supply. So here, the power supply is now going to be our output pin, pin 13 of the microcontroller, and the black is ground from our power supply. So I got more pictures, of course. I just described that. Yeah, here again is with the power supply, the black wire goes to ground here, the plus wire goes to plus there. We can use any power supply we want that does that, including our microcontroller. So here's pin 13. This is the one that's going to be a power supply on, off, not with a switch, but by control from our program. And here is ground. This ground is being shared now. It's power, so this is the ground for the microcontroller. It's the ground of our power supply, and it's also the ground for what will be our LED circuit as well. I'll say more about that in a sec. Here's the LED circuit. We've got to hook that up the way I just showed, and here it is. So the red wire plus goes to our controllable by our power supply, by our program. Our power supply controllable by our program, going on and off and on and off. The black minus wire, ground wire, goes to ground. And if our program is running, we can make this pin 13 go high and low, which makes this go on and off and on and off. And that is hello world. There are two circuits here, actually. And inside of our chip, there's actually more, but we see two circuits. There's a circle here to make the LED go on and off. there's a circle here to keep the microcontroller powered on so that it's running its program. But they share the same ground. And we can have lots and lots and lots of circuits. We can have 50 LEDs all blinking at different rates, and they all share the same ground right here, that same ground pin. It gets more complicated, but it's just 50 circuits, all with LEDs blinking on and off. There would be different pins. In this case, we only have 26 pins to play with, so we can actually only easily do 26 LEDs, but there's lots and lots of tricks to make it do lots more LEDs, but I won't talk about that today. Just know that you can do more and more complicated things to do more cool things. So again, as long as we have plus and minus voltage connected to these, current will flow, and it's guaranteed to not burn the LED out because the resistor is in series, and it can be this, it can be this, doesn't matter what it is, right? So that is the hardware for Hello World. It's called hardware because these parts are hard. You can tap on them, you can touch them. The program that runs the on the microcontroller, the program we can't touch. The program that the program controls the parts connected to this to its pins. In this case, the LED and resistor to make it blink on and off. The program we can't touch, but we don't call it software on a microcontroller. We call it software when it's on something like this thing that I'm using right here, a laptop or a phone, these more powerful ones, because the software, the program is far away conceptually from the hardware. On a microcontroller, it's really close to the hardware. So it's kind of between soft and hard. So the technical term actually is firmware. It's firm. It's not hard, it's not soft, it's firm, but it's a program. And with Arduino, it really is software. But it's still with a microcontroller, so we still call it firmware. But with Arduino, like I said a long time ago, we don't call it any of this stuff. We call it a sketch, which again, I think is silly, but it's a name you got to know if you play with Arduino. But right now, and up till now, we haven't even dealt with Arduino. We're just dealing with microcontrollers directly. When we get to Arduino really soon, you'll see that things are easier. I should drink more water so my voice doesn't go away. So here's our hardware. What about the firmware? When it's in our Arduino, it'll be called a sketch, but our program, the firmware, it's really, really, really simple. The first instruction, yeah, it's a funny name, but whatever. So the first instruction is to make this pin an output pin, the one that's connected to our LED. And that's just, the first instruction is, yo, microcontroller, pin 13 is an output pin. And now it's an output pin, okay? The next instruction is, yo, microcontroller, make pin 13 high. So now there's power there, there's voltage there. This is a power supply that is now on. And because it's on, current is flowing from the ground through here, through the resistor, through around here, and actually around here through the other circuit, and then through here, and through around and around and around and around, making energy going into the LEDs, so it's emitting red photons. In this case, it's a red LED, and we see red light. And then the next instruction is, yo, microcontroller, make pin 13 low, and now it's off. The power supply is off, so no electrons are flowing here. They're still flowing through the microcontroller. The microcontroller is still running the program. The program is over. So it's just sitting here with the LED being off because it's just sitting here with pin 13 low, so the LED is off. So that is our Hello World program. And it actually is Hello World, except we won't see it blink. Because even though this is considered really slow at 16 million times a second. That means that this LED, with using that Hello World program firmware, it will turn the LED on for a 16 millionth of a second, which is not slow enough for our eyeballs to see. It's too fast for our eyeballs to see. It'll only be on for a 16 millionth of a second. So we need to slow it down. We don't need to slow down the current. That's another thing. That's what this resistor does to make sure this LED doesn't blur out. We need to turn the LED on, wait a while, let it stay on for a while, and then make this pin low. Then, if we leave it on for a second or even a third of a second, we'll be able to see it blink. We can see down to about 30 milliseconds, even a little shorter. Different people are different, but it'll just be a little blip. So if we make this go on for a second, we can even make it go off and on and off and on. But we need to wait in between turning it on and off. And the technical term for waiting in a program is called a delay. And that's just another line of our program. So here's the program again, just written out. So the first line of the program is, yo, microcontroller, make this pin 13 an output pin. That's the one connected to our LED. Then we say, yo, microcontroller, pin 13 high. Now the power supply on pin 13 is high, and it makes the LED light up because the current's going around and around and around. And then we wait a while, like a second or whatever, and then we say, yo, microcontroller, make pin 13 low, and now it's off, and the LED goes off. And that is Hello World for real. Pretty cool. And, you know, the first time you make an LED blink, it's actually very, very exciting. And then a few seconds later, it's very, very boring. So we're going to hack on that in a bit. But before I do that, I want to show you the part that tells the microcontroller exactly how fast to go. And there's a couple parts. The older part and the more accurate part is called a crystal. And you can see on this one, it says 16.000. That means this one's going 16.000 million times a second. These two leads connect to two special pins on the microcontroller. And when voltage, and inside of here is actually a physical crystal. It's a little precision cut quartz crystal dug up out of the ground and precision cut. And when you put a little bit of voltage on here, it makes that crystal, because of the property of all the structure in there, lots and lots and lots of tetrahedrons. Bucky Fuller loves this stuff. So it makes them vibrate at exactly 16.000 million times a second in this case. You can get crystals for any frequency that you want. That's the times per second. In this case, 16.000, and you can get it as accurate as you want. The more money more accurate you want, the more money you have to spend. And in this case, 16.000. But we don't need so much accuracy in this, so we can use a less expensive part called a ceramic resonator. And this has 3 leads, the middle one being ground. So usually in modern electronics, unless you need super accurate timing, you'll see a ceramic resonator. It looks like a big capacitor, but you'll see crystals as well. For TVB-GON, we need some amount of accuracy because we need the timing to be reliable to turn TVs off reliably. And of course, we want TVs to turn off reliably, so that's why we use this. It's not as accurate as a crystal, but it's accurate enough. It's a ceramic resonator. And the frequency is, the times per second is called, it's measured in hertz, named after, what was Hertz's first name? No, I'm not remembering that either. Anyways, he's dead. So that's hertz. That just means times per second. So there it is. That's Hello World. And like I said, after it blinks a few times, it's boring. So let's hack on Hello World. Hacking is really, really fun. It's taking something that already exists or a concept that already exists and using it for our own purposes. We can change it. We can just try things and see what happens. I won't be judgmental if people like hurting themselves, and some people like other people to hurt them. So whatever, it's totally fine. It doesn't mean you're doing it wrong, but it's got to be consensual. Remember that. In general, if you don't want to be hurt, yeah, remember about polarity. And we can hack on things. If it's wrong, it probably won't work. Magic smoke can go away. But usually it just doesn't work, and you can hook it up correctly and then it'll work. Gustav Ludwig Hertz. Thank you, Claudia. But he's still dead. But Hertz is still the times per second. We can hack on Hello World to do lots of amazingly cool things. And this Hello World is the simplest thing that we can do with a microcontroller. And just with a few simple hacks, we can do lots of amazingly cool things. So let's hack this a bit. So for instance, instead of having just one output pin, we can choose another pin and make it an output pin as well. And then we can hook an infrared LED to it. Of course, when we do that, we need to have a resistor in series with it so no magic smoke goes away. And then we have this connected to that new output pin, say pin 3, and we have the short one. Where do we hook that? Got to hook somewhere because it's got to have electrons flowing to our reference ground. So it'll be another connection to ground. And now we have 3 circuits. One that'll go on and off to make the infrared LED go on and off, one to make the red LED go on and off, and one that keeps on as long as the switch is on to keep the program running, our firmware running to control the red and the infrared LEDs. We can program this, not just to blink this on and off at regular intervals, like 1 second on, 1 second off, but we can program it to have our firmware program to make this pin 3, that other output pin, make this go on and off at just the right intervals to be an off code for a Sony. And then we can blink this red LED to go on and then off really quickly, and then blink the pin 3 connected to the infrared on and off be the correct interval for an off code for the second most popular TV, which is Philips. Sony being the most popular. And then we can have this blink once, and then blink pin 3 to make the infrared light go on and off at just the right intervals to be the third most popular TV, which is Panasonic. And then blip this, and then blip this on and off to be the fourth most popular TV, which is Toshiba, and then blip this, and then do Fujitsu, and blip this to do Samsung, and blip this and do LG, et cetera, until we go through all of the off codes. And that's what TVBGone is. It's just a hack of Hello World. Kind of cool. You can do many, many more interesting things, and I'll show you some of that later in the workshop when we get to the hands-on part. Yeah, so, and by the way, it doesn't matter if that resistor is here or here. I thought I had a slide for that. Maybe I do later. So, but the thing is, Hello World doesn't have a way to tell it when to do what you want it to do. We can turn the whole thing off with a switch. But if we want to tell it when, for instance, in this case, to turn TVs off, we can use a switch hooked up to an input pin so that and have our program, our firmware, looking at that input pin to know when to do that. So let's see how that works. We add an input pin the same way we add an output pin by having one line in our program. And in this case, one of the lines in our program is, yo, microcontroller, pin 2, that's what I'll choose. Pin 2, you're an input pin. Okay, it's an input pin. And once it's an input pin, then we can look at that pin with another instruction, And that instruction says, yo, microcontroller, look at pin 2. Right now, is it high or is it low? Report back and let me know. We'll report back high or low. Those are the only choices because we're digital, right? So there's either voltage there or there isn't. It's high or it's low, on or off. If there's voltage here on pin 2 and I run that and the program comes across that instruction, yo, microcontroller, right now is pin 2 high or low? It'll report back whatever it is. If there's voltage there, it'll report back high. If it's not, it'll report back low. If it's ground, it's low. All right, so here's a wire hooked to it. I've got a black wire here. You know, the black, and I got a slide for this later, but this is just black plastic. It doesn't matter if it's black. It's just convention that black means ground and red means power. So I'm just using that convention. I have a black wire here going from pin 2, our input pin, to the ground pin, ground. And so now if I have that instruction, yo, microcontroller, pin 2 right now, tell me, report back, is it high or is it low? It'll report back to me low. And based on that, I can do this or that or the other thing. Let's look at high. How do we make it high? Well, here I've got a red wire. Again, it doesn't matter if it's red. It's just a wire hooked from pin 2 to the power pin. So right now there's voltage on pin 2. So if I have that instruction, yo, microcontroller, pin 2, right now, is it high or is it low? It'll report back high. What happens? Oh yeah, here's the different colors. It doesn't matter what color. So it can be green, it can be purple, whatever color you like. So as long as it's connected to voltage high or voltage low. But what happens if you just leave this pin blank? And I run that instruction, you know, in my program, it's doing all, and then suddenly the program gets that instruction and it says, yo, microcontroller, pin 2, is it high or is it low? What will it report back here? Well, that depends on the microcontroller. For ATmega 328P, there's a way so that it's set up so that when nothing is hooked to it, it reports back high as an input pin, high. And that's because there are built-in resistors here connected to the power supply. So that and that's called floating high. That's kind of a fancy way of saying it. It floats high. So if nothing's connected to it, it floats high with the built-in resistors. So here's just a summary. There are two choices. Either it's connected to ground, pin 2 is connected to ground, or it's floating high. We could also connect it directly to plus, but this is the way we're going to use it. And we'll do that with a switch. It's either connected through the switch to ground when we're pushing the push button switch, or when we're not pushing the push button switch, nothing's connected. So it'll look like it's high. And here's the switch. Here's a push button switch. So when no one's pushing the switch, it's like this. But if someone pushes down on that switch, then the two pieces of metal connect. And as long as someone keeps pushing, it stays connected. As soon as the person stops pushing, then the spring in the switch pops up and it's not connected anymore. And this switch has two wires. It's hard to see as part of the black, but you can see here, there's a black wire going here to ground. All right, so one side of the switch has the black wire going to ground. So this is ground. This is hooked to the yellow wire. So when I push down, the yellow wire is hooked to this one, which goes to ground. So the yellow wire is now hooked to ground. If I let go, boop, it's no longer hooked to ground. But where does the yellow wire go? It goes here to pin 2. So when I'm pushing on the switch, the black wire is connected to the yellow wire, which is connected to pin 2. Pin 2, while I'm pushing the switch, is connected to ground. And when I let go of the switch, boop, the yellow wire is not connected to anything except pin 2. So pin 2 connected the yellow wire to nothing is floating high. But when I push the switch, it's connected to the black wire, so it's ground. I let go of the switch, it's connected to the yellow wire, which is going to nothing, so it floats high. Ground, high, low, high, low, high, low, high. Okay, so that is what we see. So what we want to do is have our program look at pin 2 every now and again and report back if we're seeing low. If we're seeing low, that means someone's pushing the switch. That means someone wants us to do something. So let's do that cool thing when someone pushes the switch. So that's the way the switch works here. So I went through all that. So here, without all the messy different wires, is our hardware. A red LED, so that, I actually never mentioned that, and it's kind of important. Maybe you figured it out, but we have the red LED for TV Be Gone because we humans can't see infrared. The video camera in the video I showed you showed the LED blinking, but we can't see it. So we want the red LED to be blipping so we know that TV Be Gone is working and doing its thing and trying to turn TVs off. Because it might take up to a minute to turn all the TVs off, and we want to be sure that we know that TV Be Gone is still trying. So it's blipping, we blip this, then do a code, blip this, do the next code, blip this, do the next code, blip this, do the next code. So this is hooked to one pin 13, through one of these resistors, so no magic smoke goes away. This is hooked to another output pin, which is going through a resistor, so no magic smoke goes away, which is pin 3. This is going between ground and pin 2. And here is our firmware. And so the firmware conceptually is actually quite simple. It's just a hack of Hello World. It's a little more complicated, but it's just the same thing going on with Hello World. We have 2 output pins, so we gotta go, yo, microcontroller, pin 13, that's output. Pin 3, another line is pin 3, that's an output. And then we have an input, so we go, the next line is pin 2, that's an input. And then we have this line here, which is waiting for someone to push the switch, meaning that pin 2 is low. We wait for pin 2 to be low. When it's not low, we just sit here waiting. But as soon as it's low, we come down and do all the rest of this stuff. So we blip the red LED, then put out an off code. Blip the red LED, put out another off code. Blip the red LED and then put out the next off code, et cetera, et cetera, et cetera. It takes a minute to do all those off codes, but then it does all of them. And then actually, what it does is put itself into a low power mode to not use up all the batteries, waiting for you to push the switch again to do all this again. And I'm not going to go over how low power mode works, but that's the whole thing. Low power mode is just a few lines of code which you can copy from other projects, including TV Be Gone. But let me just say just a little bit more about how this works, because this is actually 2 lines of code, not just one. So what this does is it waits for pin 2 to be low, but what it does is look at pin 2. So this is it. The line of code is, yo, microcontroller, look at pin 2. Is it high or is it low? Okay, so it reports back high, meaning no one's pushing the button. Okay, so we don't get to do anything cool. So we go back here to this instruction and we go, yo, microcontroller, pin 2, is it high or is it low? Oh, it's high, no one's pushing the button. So then it goes to the next line, which says, no one's pushing the button, so come back up here. And then it goes, yo, microcontroller, pin 2, is it high or is it low? It reports back high because no one's pushing the button, so we don't get to do anything cool. So we go back here. Yo, microcontroller, pin 2, is it high or is it low? Oh, it's high, we don't get to do anything cool. Go back here. Yo, microcontroller, pin 2, is it high or is it low? It's high, we don't get to do anything cool. Go to the next instruction. Go back up here, let's try again. Yo, microcontroller, pin 2, is it high or is it low? It's high, we don't get to do anything cool. Back up here. Yo, microcontroller, you get the idea? We get bored with that kind of stuff very easily. But microcontrollers never get bored. It can do that hundreds of times, thousands of times, billions of times. As long as the program keeps running because there's a power supply, it will keep doing that. Years, decades, it'll keep doing that. But as soon as someone pushes the button, then as long as someone's pushing the button while that instruction gets executed, it'll go, yo, microcontroller, is it high or is it low? It'll report back low because someone's pushing the button. And we'll go, yay, that next instruction just lets it go down. And then we do all the cool stuff, which is turning TVs off and making the world a better place for everybody. Cool. That's how TV Begon works. That is a hack of Hello World, and it's how TV Begon works. And if you can understand that, and you don't have to understand all of it and have it totally clear in your head, I want you to have a feel for how this stuff works. And if you have a feel for how this works, that can give you enough confidence to download this project and others and try it and see if you can make it work. And you can, because it's actually really simple with just a little bit of playing around. And you'll make mistakes, of course. We all make mistakes. Even, I've been playing with this stuff since I was 6, and I'm way older than 6 now. How old am I? 63, I think. I don't know. I can't do math right now. So I've been doing a lot, and I still make lots and lots and lots of mistakes, and I keep learning from mistakes. So, but you can try this stuff. This is TV Begon, except it's not a very good TV Begon because it won't turn off TVs for very far away. And this brings up my last part that I'm going to show you, which is an important one. This doesn't turn TVs off from very far away because the power supplies, output pins, our power supplies controllable by our program. We can turn them on and off, controlled by our program, but they're not very powerful. They can't push electrons out of the pin very quickly. They can't supply much current. That's just another way of saying it. Because there are resistors built into the microcontroller so that it keeps magic smoke from going away easily. And these chips are super, super, super robust. It's very difficult to burn them out by accident. You have to try. You seriously have to try. You can hook up the power supply backwards and keep it on there for like minutes. This gets hot enough so that if you touch it, you'll get a blister. And then it cools down, you hook it up correctly, and it still works. It's kind of amazing. But anyways, they're built-in resistors, so it can only make this infrared LED light up so bright. And we want it to light up on and off and on and off as bright as possible that they're allowed. And TV Begon, I have the best infrared LED as possible. So on very little current, it can turn off TVs from far away, but I have to give it like an amp. And with this, it can only give it about 20 milliamps, 0.02 amps. So we need a current amplifier. And if we add a current amplifier, then we have TV Begon for real. And a current amplifier is what a transistor is. Yeah, just review this for a second. LEDs, if we only have a little bit of current, it's dim. If we can add more current, it's brighter, more and more and more until it burns up. We want to give it as much as possible for the infrared LED on the TV Begon so that it's as bright as possible without burning up, so it can turn TVs off from far away. And let's see, no need for that. Yeah, so a current amplifier. One of the functions, very popular function for a transistor, is a current amplifier. There's lots and lots of different kinds of transistors, and they're actually very bizarre devices. But this kind of transistor, when used digitally, even though they're very complicated and they're quantum, they're very easy to use. There's 3 pins, three leads: ground, in, and out. Ground goes to ground. It's just yet another connection to that ground pin. In goes to, this connects to the output of the microcontroller. Instead of the infrared going directly to the output of the microcontroller, we take it off the microcontroller and we put that on our output pin, and we hook this to the input pin. But of course, there's an extra resistor that we need to make sure no magic smoke goes away from the transistor for the input pin, and I'll show you that. But before I show you the picture, let me just tell you about just some bizarre stuff with quantum and transistors. Transistors don't work with classical physics. According to classical physics, transistors are electronic barriers that can't be crossed. So they're devices within which particles that don't exist go through barriers they can't cross. That's why we don't use quantum in everyday life. It's kind of bizarre, but transistors do work, and It's kind of cool to study that stuff, but I won't talk about that anymore. So yeah, here's all the stuff. It's exactly the same as it was before. The firmware is exactly the same. The only difference is we've added one transistor and one more resistor. And this goes in series with the input pin to the output pin. And that for real is TVBGON. And if you have a feel for what I've gone over, then that is everything you need to know about electronics. Any questions before I go into the important part of the next important part, which is Arduino? A couple people are typing. What's the difference between a brand name battery and a generic battery? Generic isn't necessarily bad, and brand names aren't necessarily good. But in general, Everready and Duracell and GC and a bunch of other brand names have better chemical processes, and they also have a better seal on the battery so that as the battery wears out and gets older, they don't leak their chemicals, and battery life can be longer. So yeah, but there are a lot of good batteries out there in the world. I try to use them as little as possible because they are toxic waste once they're over. And using rechargeable ones means that the toxic waste goes in the landfill less frequently, longer duration, but yeah, it's just part of the reality of things. Any other questions about what we went over? What's that? A few things. How do you know if they're transistors? The transistor has numbers written on it, so they all have names as well. The most common names in the United States, the US kind of numbering names for transistors are 2N, N as in Nancy, 2N, and then some numbers. And you can look that up on your favorite browser and get a data sheet. In Europe and other places, they have other kind of numbering systems, but you can look at the numbers. There's other numbers besides the name, though, is the thing. There's a date code for when the manufacturer made it and other stuff. So you can try searching for those numbers and see if any of them come up as a transistor or a part number. As you play around with it just a little bit, you'll get used to the numbering, the naming kind of conventions. Different kinds of LEDs, but the same color? Yes, indeed. The color of the LED, like here's a red LED, but it's not red because the plastic is red. It's red because of the quantum physics of manufacturing this thing. There are LEDs that have clear plastic, colorless plastic, and yet it'll be red or blue or infrared, etc. So you can't tell, and the name of the LED is not on there. It has to be on its packaging. So you want to make sure that if you have a bunch of different LEDs that you keep them segregated so you can tell which is which. What did I miss? You have to keep updating TVBGON codes. Yeah, about once every year and a half I update it. All the old codes still work from way, way, way back when, but every year and a half or so there's a handful of new codes that I add. And yeah, so how do you know how much power is too much for a component? That's in the data sheet. And I won't go over too much about that because reading data sheets takes practice. Any project that you download, hopefully the person either read the data sheet and understands it, or they got the information from some other person who got it, or got it from someone who got it from someone, etc. Because with all the sharing and open source projects around, this stuff is well understood by at least the roots of the projects, and they just get passed along so everyone can benefit from it. Did I miss anything? An LED is a diode, and a diode only allows current to go one way. Why does an LED have a second pin? Oh, a diode has two wires. We have to have two wires. We have to have at least two wires on every part. Let's see, where is place in here? Yeah, so current goes in one of these leads and out the other. So one of the leads is the in and the other is the out, and we call it minus and plus. It doesn't matter which way the electrons are actually flowing, because in actuality, according to quantum, they don't even exist. They only have probabilities of existing. So, but just, think of it sort of like water flowing through pipes. You need two sides to the pipe. So electrons are coming in and out, and they're being pushed by our power supply. But they're only flowing in one direction. That's the main thing to know. And you need one side connected towards ground and the other side connected towards power. So yeah, so it looks like you got that. TV Gone is several years old. Do I need to buy a new one to get new codes, or can I update it? Unfortunately, in order to keep TV Gone as inexpensive as possible, I use very inexpensive microcontrollers. And so they're not reprogrammable, unlike Arduino microcontrollers. The ATmega 328Ps, which Arduinos use, can be reprogrammed again and again and again. The most inexpensive microcontrollers can only be programmed once. And at the factory, we program them in mass all at once, and then it's way cheaper. So unfortunately, you can't reprogram the TV Gone, but it's still good for billions of TVs out in the world that need to be off. So please use it and turn those TVs off. If you don't do that, who will? So yeah, so you don't need to update it. But if you want to, they're still available. And of course, the codes are here, and I update this code, and you can reprogram your TV Gone done with the Arduino or TV Gone kit, because the TV Gone kit has a reprogrammable one. Was the input pin for the transistor into pin 2 from the example? Yeah, so hold off on that. Just kind of know that there's the current amplifier between the LED and the microcontroller, just kind of conceptually. When we get to the schematic very near the end, you'll see explicitly, if that's okay. Cool. So that's the end of this section of slides. So let me get the next section of slides in here. Okay, update, Zupa. Get the first slide. Okay, now this is the part in the workshop where normally people learn to solder, but we're not going to do that here. We're going to, and they solder get your own Arduino. But if you have an Arduino, it's the equivalent of getting all these parts and putting them together, except someone did that for you, and you get a working one. And if you put it together, and then there are all these pins on the side. Let's see. I'm in Berlin, where it's now 6:45. Let's see, what time does the workshop, how much longer do we have for the workshop? Can someone tell me how much time is left? Thank you for typing that. 3 hours total. An hour and 50 minutes? Okay, great, perfect. That's what I planned, so that worked out well. I didn't keep track of time, thank you. So you see the Arduino, whether it's a clone or whether it's a official Arduino or whatever, they all have these pins on the sides where you can push a wire into or a part, which make it really easy to connect to the pins. So if I hook this, like here's this blue wire hooked into that hooks to one of the pins on the microcontroller through the board. And this red wire also goes to one of these holes, and that through the board is connected to another pin. These happen to be the power and ground pins. And yes, I go directly from this workshop to my next workshop directly, which is RG Touch, which shows how to solder. So if anyone wants to go to that one, it's another room, another big blue button room, and I'll hopefully me or Serge or Tom will post that here at the end if you want to do that. But let's get back to this. So yeah, all of these holes connect to a pin of the microcontroller. All you have to do is push a wire into there or a part, and it connects that wire or part to a pin of the microcontroller. In this case, the red and the black supply, and it's connected through here to the power pins of the microcontroller. And if you then turn the power supply on, then it runs the program that's in here. And that's normally a video, but let me now get this back video on. Start sharing. I have phones, so I can do some close-ups here. Phones with video. Let's see if that works. Yeah, it's working. There can be many of me. Let me turn this one on too while I'm at it, because you can get different perspectives. Start sharing. Look, there's lots of me. And you can see my shirt, which is one of my favorite shirts. This is a shirt from the hackerspace Rev Space. Rev Space is a hackerspace in the Netherlands. And it's just a nice shirt. I don't know, can I make it? It's hard to do this because everything's like mirror imaged and all this stuff. So anyways, enough of that. I'm going to actually do this here. So where is... Well, that's hard to do. Let me turn up the brightness so I can actually see what I'm doing. Yeah, so ground. Yeah, and you can see here's my power supply. And I have red and black wire. And I'm going to plug this one into, let's see, there's the black wire. And I'll do the red wire into the 5-volt one. And then I'll turn the power switch on here. Let me zoom out a bit so we can all see what happens. Let's say that's not it. Here we go. And this is what comes pre-programmed in the, wait, where's my, there it is. This is what comes pre-programmed in the microcontroller for the Arduino. So it's just fancy LED blinking, right? So we can hook things up to these other holes as well. So let me put that down for now. Go to the next slide. Once we know the Arduino is working, we can program it. There's different ways of doing that depending on the different. Let me not do the Arduino. I'm going to use this now, which is, let's see, camera again. This is another clone. All right, so wow, getting that perspective is really weird. With these cameras, everything is mirror imaged on my screen, left, right, up, down. How do I? Okay, there we go. This is an Arduino clone. So I'll hook this up here. I can do the same thing with power and ground. And this one just has one LED instead of several. But you can just see it's blinking. The other LED that's always on is just to tell you power is happening. This one has a USB controller chip built into it, which is this chip here. You can see the ATmega 328 right here. But on the Arduino, take a look at the slide. There's no USB controller chip there. It's external. We have it here. So this is originally made by a company called FTDI. They're kind of slimy. A lot of people have come up with alternatives since then, and we use an alternative here. This is a really cheap USB, inexpensive, but really good USB serial chip. These are sold really cheap in China, really cheap in China, but they don't have the correct pinout for standard Arduino kind of projects. So my friend Tully and I came up with this green board, which converts it, and then with that you can hook it up to a regular Arduino project with these pins and a cable, and that's what I showed in these next slides. But with a more normal nowadays, since everything's just so cheap, Arduino board, you can just use a regular old connector cable, just regular USB cable. And if I hook that up to my computer, then it's powered through my computer's power supply, and I don't need the batteries. But once I have it connected to my computer, then I can program it. And once it's programmed, then I can disconnect it from my computer and hook it up to batteries and bring it all over the world, and it's portable. Some projects you might want it always connected to your computer, because you can have the Arduino actually communicate with your computer and send data back and forth. And it can also be online and all sorts of interesting things. Or it can just be standalone on its own, run by batteries. I'm going to show you some stuff you can download. So my workshop page on my website, you can get to with this URL, shortened URL, and it's case sensitive. So uppercase A for TN, Arduino for total newbies. That's what it stands for. So you can get to the workshop page directly, or I'll just show you quickly how to get there. Cornfieldelectronics.com is my website. And this is on the slides, which I'll show you how to download later also. If you go to the projects tab, and then scroll down, you'll see this picture, which is the first time I gave this workshop, which was at Noise Bridge, where I taught 50 people about Arduino all at once and how to solder. And then the last link under there is the workshop web page. And if you go there, then you get the exact same picture, but it's the Arduino for total newbies workshop page. And there, if you scroll down, you'll see stuff you can download. Okay, so let's see. Maybe I should screen share. I'll do that a little bit later. So if you go to the first one, that brings you to the Arduino page, where you can download the latest Arduino software for free. It's also open source. And if you need a driver for your USB serial chip, whether it's on the board or in a separate cable, here's the ones I use. And then FTDI, the original company, here's their links. There's other ones too. And a driver, for people who don't know, is a way to tell your operating system how to deal with external hardware. The operating system comes with drivers for your keyboard and mouse and screen and all that stuff, because it's built in, but some external hardware it doesn't know about, and you've got to tell it, and that's what the driver does. So that's what that is. The next one is, if you want to make a TVBGON actually work, you need the TVBGON firmware, the sketch that runs on an Arduino. And then lastly, there's the schematic, which looked scary at the beginning, but I'll show you is very simple. And then at the bottom are the slides. So that's where you can download the slides. And that includes all the assembly instructions, soldering instructions as well. I took them out for this. Thank you for putting it in the shared notes too. So here's what the Arduino page looks like, and you can download this for Windows, Mac OS, and Linux. Linux, by the way, has pretty much every driver built in for USB serial chips, but Windows and Mac doesn't. But you need different software for the Arduino software. You can just choose Mac OS, Windows, or Linux. Here's that was a driver page. When you do the TV on Sketch, it'll be a zip file, and then you can store it on your computer anywhere you like. If you put it in the library folder for Arduino, after the Arduino software is installed, then it shows up conveniently in your example menu, which I'll show you in a bit. And then here's the schematic, which might still look scary, but won't pretty soon. There's that. To hook the external one up, if you have mine, you have to have this cable, and it just goes straight across. You just want to be sure that the markings here, which says ground on this side and RST on this side, go to ground and reset. But for your normal Arduino, you don't have to worry about that, because it's just, here, let me put this here again. You just hook this up. And then with the other end, this goes to your computer's USB, and then it's done. You don't have to worry about orientation or anything, which is very convenient. Yeah, so once you have the Arduino software installed, and it's super easy to install. You double click it and it works. Occasionally, Mac OS being Mac OS, you have to do it twice because Mac OS is Mac OS, but twice at the most, and it'll just work. And then you have to do two things to set it up the first time, and the first time only. Okay, and then it remembers your choices. If you'd use another Arduino board, you've got to do it again for that Arduino board. But as long as you keep using the same Arduino board, you only have to do it once. And you can do it months later, it'll still be there. But this is what you have, the two things you have to do to set up. So the first thing is tell it which board. So if you go to the File menu here, or Tools rather, Tools menu, and then down to Board, and then it shows you all of the different boards that Arduino has ever made. If you have a clone, you have to know what it's a clone of, a copy of. What I'm going to be using today is a clone of Arduino Uno. So I chose Arduino Uno. You click here, and then all that disappears. And then down here in the corner, I don't know if it's too small for you to read right now, but it says Arduino Uno. Then the next thing you have to do is tell it which serial port. So the driver that comes with Arduino or that you installed tells your operating system that there's a serial port, and that used to be the only way you could get stuff in and out of a computer. And before that, it was a parallel port. But serial ports are still useful, and they have names. The operating system gives it a name. In Linux, it's really easy. It'll be USB TTY0. Unless you already have one, it'll be USB TTY1. Unless you have two, it'll be USB TTY2. But probably it'll be USB TTY0. If you have Windows, it'll choose a number for you, but it starts with COM, C-O-M, and then a number. And the operating system chooses that number. So in my case, the operating system chose COM3. And if you have Mac OS, it'll say USB TTY and then a whole bunch of hex numbers, a whole bunch of letters and numbers. And but the important thing if you have Mac is that it'll say USB serial or USB TTY, depending on if you have an older system. There will be other choices as well. It'll say Bluetooth and maybe some other stuff, but those aren't for your Arduino. The one for Arduino, if you have your driver installed correctly, it'll say USB serial or USB TTY. Okay. Cool. Next slide. So yeah, when you install Arduino and it's all set up, the first thing you see is this minimal screen. And one of the things that makes Arduino really cool and easy to use is that it comes with lots and lots and lots of examples for you to use that make it easy to hack. The examples are very well documented, and you can modify it and just see what happens. You do not need to have ever programmed ever before to be able to do that. And I'm going to show you now how to do that, even if you've never programmed anything ever before. And to do that, I need to share my screen. Oh yeah, before I do that, just you can see here, to get to the examples, you do the File menu, and then go down to Examples, and then all of this shows up, and you've got all these categories of examples. In Basic, you've got Blink. Blink is the hello world of Arduino. It makes the LED that's built into the board blink. And all Arduino boards, unless there's certain obscure clones, have a built-in LED that blinks. And it happens to be pin 13, which is why I kept choosing pin 13 in the examples earlier. So once you click that, then you get the blink program appears. Okay, so now I'm going to share my screen, and this uses up a bunch of bandwidth. Tell me if my audio starts getting weird, but let's see, where's my, okay, yeah, so I've got share screen. Huh. Got to choose the right, oh, I'm not seeing it. Do I have, yeah, Arduino is there. I'll just share my whole screen. Okay. You're going to see an infinite loop of video. Oh, error, screen was not granted. Oh, by canceling it out, I messed that up. Damn. Okay, so, hey, Serge, I'm going to get out and back in again, and you'll have to make me a presenter again. You cool with that? Serge? Hello? Or Tom, are you there too? Can anyone hear me? Okay, good. Yeah, so Tom, I'm going to go out and then come right back in. Please make me a presenter when I get back, okay?
All right, which one are you going to be on? Mitch 1, Mitch 2? What's?
Oh, that'll be Mitch Altman.
Okay.
Okay. So
Okay.
sorry about that, folks. I'll be right back. And I don't know what happens with the recording. Maybe I'll pause the recording, and then I'll leave. Great, thank you. And so there's this text on the screen in the hello world, which is Blink. Blink is the hello world that comes with the zillions of cool examples. It comes with the cool examples with Arduino software. And there's different colored text on the screen. And most of the text is not code. It's text for you, the human, to be able to understand the code. And that's called comments. So comments, if you're a good software geek, then you write lots of comments no matter what. And if you're not, oh, did my video just go away? Yeah, my video just went away. That's weird. I gotta re-enable it. That happens on Big Blue Button sometimes. I'm not sure why. Reallow. Yeah, so if you're a good software geek, you put lots of comments. And if you're not a good software geek, if you're a terrible software geek, you don't put comments because you think you'll understand it later and you won't, and no one else will either. So I will take your software geek card away from you if you don't use comments. But anyways, on the examples, there's lots of comments to tell you, the human, whether you've programmed ever before or not, what is going on in the program, how the code works. So the comments are gray. So like, for instance, I'll highlight them here in orange, but these are comments. And there's lots more up here too. So comments in the programming language in Arduino start with /* and end with */. That's one way to do comments. The other way, which is a little bit darker gray comments, they're still comments, is // and everything to the right is a comment. They're same comments. You can do it either way, it doesn't matter, and the examples have both in it. Usually though, the // and what happened? These kind are a section to describe the beginning or a section of code, whereas the // is a way to tell you about a specific part of the code. And while I'm remembering to talk about this, the code on that runs Arduino is actually C++. That sounds scary, the Arduino people thought, to non-geeky artists, so they don't call it C++, just like they don't call it a program, they call it a sketch. So the sketch is written in wiring. That's the name of the programming language, but it's actually C++, with a bunch of pre-written high-level functions. That's the sort of technical thing, but there's all this really low-level stuff that you don't have to deal with. You just use one line of code and it does all this stuff for you. And that's one of the things that makes the Arduino wiring program really cool, but it really is just C++. Okay, so there are two sections in every Arduino sketch program. So there's setup and loop. There can be more than two, but there's a minimum of two. And in each section, there can be 0 to thousands of lines of code. Okay, but you need the two sections even if they're empty. You can have more sections as well, but on minimum, you need two. So the hello world, the simplest one, has two. Each one has at least one line of code. So here, the setup has, let me do it with my cursor. So setup has one line of code, non-gray line, only one. And you can see it's called setup, okay? And down here, this is loop. This is the loop section, and it has 4 lines. Okay, so right now we don't know what they do, but the comment sort of tells you what the section does. Above here with the // it's dark gray. It says setup runs once when you first turn your Arduino on or press reset. And in any computer, pressing reset is exactly the same as turning it off and on again. So when you first turn your Arduino on, it does what's in setup once. In this case, this one line of code. And this comment gives you a clue, but don't look at that necessarily yet. It'll do this line of code once and only once, and then it comes down to loop and does what's in here again and again and again and again until you turn the computer off. And this line of comment tells you that. The loop function runs over and over again, well, not quite forever, that's a long time, but until the battery runs out or the internet dies or whatever. So yeah, so it'll do these 4 lines of code again and again and again. So what happens here? Oh yeah, so the comments at the top, there's a bunch of credits mainly, but it's the name of the program, blink, and then it tells you what it does. It'll turn on an LED for a second, then off for a second, and then repeats. That's what blink does. And that's what we see happening here. right? So that's already in this Arduino that I have. But how does that happen? Well, we already went through this. You're not following what I'm talking about. Yeah, so I've got different video on the top, just so you're aware. I've got 2 cameras with video that I can do close-ups, plus there's the video of me talking. So one of the videos to the right of me talking, or maybe left or right, depending on, but can you see the LED blinking now on one of the other videos at the top? Yeah, cool. So that's what I was talking about. Sorry, that wasn't so clear. But now look at the main shared screen again. This is what we went over before. What do we need for Hello World? We need an output pin connected to an LED, and then we need to make that output pin connected to the LED go high for a while and then low for a while, and that makes the LED turn on and off. That's what we do here. For setup, software geeks would probably call this init or initialize, because it initializes all the things just when you need it at the beginning of the program, and then you never need that stuff again. It just goes down and does all the nitty-gritty of the rest of the program, which is what's done in loop here. So the thing we need to do once is create an output pin. And that's what this weird looking line does. If you've programmed C before, this shouldn't be too weird for you, but it's still, C is kind of complicated. So, and there's uppercase and lowercase, and it actually matters if something's uppercase or lowercase. So little p, little I, little n, big M, little o, little d, little e, parentheses, LED underscore built-in, comma, output, parentheses, semicolon, and semicolons are important too. But if you've never programmed C or anything before, don't worry about it. It's actually easy to hack once you see what this does. And the comment above it with the / in dark gray tells you this initializes a pin, a digital pin, because we're in computer land, to be an output pin. And the name of that pin is called LED built-in. And our Arduino always has a built-in LED on pin 13, and the name of pin 13 is LED built-in, LED underscore built-in. Okay, so this makes the built-in LED pin, it makes it an output pin. That's what this line does. Okay, so pin 13 happens to have a name. It's called LED built-in. But let's say I also want to have pin 3 be an output pin. Can you have any idea of what I would do to have pin 3 also be an output pin? Well, I can copy this line and I'll paste it in here. This makes LED built-in pin output pin twice, but yeah, you got it. Not high. High, it comes later. This is just making it an output pin. So what I just typed here, pin mode 3 output makes pin 3 an output pin. Okay. And let's say I also want an input pin. Let me copy that, and I'll make pin 2. I'll add an input pin, which is pin 2. It's not an output pin, it's an input pin. Yeah, 1 and 2 are blank right now. When I need them, I'll let you know. And that's when I'll show you about wiring things up. But for now, just the shared screen and my beautiful face. So yeah, so anyways, this is a way to hack Hello World to do more than what it was intended to do originally. But let me Control Z to get rid of those. Okay, so there we go. So that's how the setup section works. Oh, shared screen is not updating?
Yeah, it's not for me either.
Oh, scheisse. Let me go back in here. Do you see a red dot moving around on my... Oh, it stopped sharing. It stopped sharing. let me share entire screen again. Allow. When did that happen? Recently or a long time ago?
I think since you came back.
Since I came back.
I believe so.
Well, let me go over that really quick again, because it'll make more sense. So can you see the screen now again?
Yep, you're good.
Okay, great. So at the top, you see the name Blink, and it tells you what it does in the comments. And now I'll scroll down further. Here's the setup section, and it has one line in it. And here's the loop section. It also has one line in it, or 4 lines in it, 4 lines. And the comment above setup tells you what it does. It does it once. The loop section, the comment here tells you what it does. That again, the comments are just there for you, the human, to read and understand what the code does, because the programmer who wrote this cared about you learning from it, and also cared about the programmer coming back a week later and understanding what the programmer did. Okay, so here's pin mode and all that stuff. I can copy that, and I can add another output pin. Right now it's the same, but let me get rid of LED built-in has a name, but pin 3 doesn't. So right now I have the built-in LED pin, which is 13, is an output, and now I have also pin 3 as an output. And I can come down here and do that again to add an input pin as pin 2 is an input pin. Right? So now I've got 2 output pins, 13 and 3, and I've got an input pin. But for Hello World, we don't need all this stuff. So let me Control Z out of that. And look at what happens with inside of loop. So this is where we turn the LED off and on. So you can see here this line with digital write, that writes to the output pin either high, like this line, or low, like this line. And that's really just turning the output pin on or off. And you can see the, let me just scroll over here. This line is high, and this one is low. But what is going high and low? Well, the output pin with this name. If I had, if I also wanted to do, another LED that's hooked to pin 3 and make it low right here, I could do that. The comments are wrong now, but there it is. I can make pin 3 low by doing that, but I'll Control Z out of that as well. Okay, so this makes the built-in LED high. And look, the comments over here to the right, the dark gray, turn the LED on by making it high. Then the next line, wait a second, and that's this delay. Then we turn the LED off and wait a second again. These are units of time of how long to wait before going to the next line. Okay, so this line takes 1,000 units of time, then it does the next instruction. The units are milliseconds, thousandths of seconds. Okay, and 1,000 thousandths is a second. So we turn the LED on, we wait a second, turn the LED off, wait a second, then it comes back to the top of loop, and it does this again and again and again and again until we turn the power off. And in technical terms, anything that's done again and again and again and again in a program is called a loop. And the Arduino people kept it that. They didn't change it to something silly. Cool. So this is just text on a screen. How do we get that from text on a screen into, okay, so I'm going to use my phone again. So here's my Arduino. It actually has this program in it already. But how do I get the text on my screen? Here's the text on my screen. How do I get that through this cable and into here? All I need to do is press this button here. And see, when I mouse over it, it lights up. And then it says upload there. Upload. If I click on that button, I'll put the phone down for a second. So I'll click on that button. Then you'll see that all this magic happens. It converts the text on a screen that's actually code into a form that the microcontroller understands, sends it through the USB and all that stuff into the microcontroller's memory, where it then runs. Okay? And that takes just a few seconds. So I'm going to click it right now. Now look down below, you can see some messages. It says right here, compiling sketch. Okay, and here's a progress bar on the right, this blue bar here, compiling sketch. Compiling is converting the code into a form the microcontroller understands. When it's done with that, it will say uploading. Uploading means it's sending it to the microcontroller's memory. And once it's there, it'll say here, done uploading. Uploading, now it's uploading. And now it's done. That means it's running. And let's look at my phone camera again, and there you can see it's doing the same thing because it just put the same program back in, but it did it. Okay, so, but that's all there is to it. Pretty cool, isn't it? So let's hack on this a little bit to make it do something different so we can see the effects on the board. So I'm going to make this go, yeah, just a few lines of code. And this is the easiest code possible. And it's really, really small. It's only about 1 kilobytes of code, unlike most modern programs on your computer, which are hundreds of megabytes. So, but let's make the LED blink 10 times faster. What do I need to do to make the LED blink faster? I can hack on these lines of code. What do I do? Can you think about that? Yep, you got it. Change the delay. So I make the LED high, it turns it on, then I wait just a short amount of time, 1/10 of a second, and then I make it low, turn the LED off, and then wait 1/10 of a second, and etc. So I'll just come here and do that. Okay, so now I'm going to, but this is just text on a screen. You can look at my board. It didn't change the board at all. The text on the screen needs to be changed to a form the microcontroller understands, and then sent through the USB into the microcontroller's memories. Will then do this. And to do that, I have to go to the upload button. Again, look on the shared screen, the upload button. I'll click on that. And now it says down in the blue bar down at the bottom, compiling. You can see the progress bar. My computer is going really slow. This usually takes like 3/4 of a second, but I don't know, Java, who knows? And even though Arduino uses C++ wiring, the Arduino program itself is written in Java. So you can see it says compiling sketch. And it's going through this information here. And then after it's done, or now it's uploading. Before it, oh, let me make this bigger again. Let me just point out one thing. I'll scroll up here. You can see it shows you how big your program is. Oh, it's using up hardly any RAM. I've got almost all 2K of the 2K left. It uses up 2% of the program storage, which is 32 megabytes. Earlier I said the wrong number. It's actually 32 kilobytes, 32 kilobytes. It's using 922 bytes out of the 32 kilobytes. Okay, so let me bring that back down again. Okay, but now look at what the board is doing. And all that happened automatically just by clicking the upload button. Cool. So you don't have to make both of the on and off times the same. Let's make it so that the built-in LED on the board blips once, just like a 1/10 of a second on off, waits a second, blips on off for a 1/10 of a second, waits a second, etc. So to do that, I'd make the off time longer again. But again, that's just text on a screen. In order to make that happen on the board, I click the upload button, which I'll do now. Question about how to estimate RAM. With Arduino, you can't. You just have to try it and see. If it runs out of RAM, it'll tell you that there's an error. And you can just try again. That's kind of one of the disadvantages of real programming. It's not like a real programming environment, but you can do so much with it. And my RG-Touch music synthesizer is super complicated, and we've done a lot with it. So you can use this stuff to do pretty intense projects. Okay, so it's uploading, and you can see now that it's blip, blip, blip. If you look on the video above my shared screen. All right, so so that's cool. We've hacked Hello World, the Blink program, to do things different than the original programmer intended. The original programmer, whose name is Colby Newman, I guess. Oh no, modified by lots of people. The original program was Scott Fitzgerald, modified by all these different people. But it was intended to only blink the LED on the board on and off for a second each. But we've changed it. We hacked it to do what we wanted to do. The question about how to stop a program, you turn the Arduino off. That's it. You can reprogram it again, and then it'll have that program in it for as long as the world exists, guaranteed 15 years at least, according to the manufacturer, and or until you reprogram it. Okay, so how do you make it control things external? Well, here is an LED in my hand. I want to make this LED blink. Can you see the video above my shared screen? I want to make this blink. I'm going to leave the shared screen software, firmware, sketch the same, but I'm going to make this LED blink. Let's look over here. I don't know, can you read these numbers? Let me go back to my presentation, actually, where you can see it better. Let's see, stop sharing. Okay, there we go. And I'll go back to slides and okay, so here's Arduino, but same for all Arduinos. They have these holes like I showed you before, and they're labeled. Here's one labeled 13. That goes to pin 13 of the microcontroller. If I hook an LED to pin 13, I can make it go on or off, controlled by the same sketch that's already running in here, or another sketch for that matter. But I need the LED has two leads. One goes in pin 13 and the other goes to ground. And it just so happens that down here is it's labeled ground right next to pin 13, just kind of nice for us in this case. Which goes to which? Pin 13 is going high and low. Ground is always low. So I got to be sure that the short minus ground lead of the LED goes to ground, and that the long one goes to pin 13. And you got it, Bob. And so I'm going to do that here. And now I'll show you what's happening with the other video. Oh, can other people see my video? Which is this? This is Mitch's phone, phone 1, the one all the way to the right on my screen. Can you see the LED blinking? Yeah? Okay, yeah, on my screen it looks black. So I'm glad you can see it. But you can see that external LED right here is blinking the same as the internal one. They're both hooked to pin 13. This one's just way, way, way brighter. And again, I cheated. I do not have a resistor in series. But there's those built-in resistors in the Arduino, or in the microcontroller, the ATmega328P. You don't want to rely on those in general if you're doing a real project, but we can do that here just for demo purposes. But there's no pins to allow me to put things in series here. It's really cumbersome. So that's why we use a solderless breadboard, which I'll show you next. Okay, but let me take out this LED here. I'm going to take this out. Okay, no longer connected. But I happen to have here a motor. Here, let me show it here. Here's a motor. And I put just some tape on it so you can see when it spins. And I've got 2 leads on the motor. When I put voltage on these 2 leads, the motor will spin. When I take voltage away, it doesn't spin. So I took the LED out, but I can put this motor in instead. So when the sketch believes that it's turning an LED on the board on, what's actually going to happen if I put this into pin 13 and ground, the motor, then what's actually going to happen is it's going to turn the motor on, and the motor will spin for 1/10 of a second, and then wait a second and it'll stop, and then spin for 1/10 of a second and off, etc. So let me do that. Just do pin 13 and ground here. And look what's happening for the motor. Cool, huh? So this is Hello World being hacked to not only blink LEDs, but make something move. And imagine hacking this a little bit more. So I have 2 output pins, each connected to a motor. And each motor has a wheel, and the wheels are connected to a robot, like a simple little robot. I can have a simple robot controller just by hacking Hello World. If both motors are on, then it makes the robot move forward. If only one is on, it'll move right. If only the other is on, it'll move left. Just by hacking Hello World. This is super easy and fun. So now I've got another part here. That is a speaker. It also has 2 leads. 2 leads. There's no short and long. I'm going to put this in pin 13 and ground. Now thinking about this is a little bit more complicated, because when a speaker isn't really considered to be on or off, but still when I put voltage across these 2 leads, it sort of turns the speaker on, which is an electromagnet surrounding a permanent magnet. An electromagnet is a coil. When current goes through a coil, it makes an electromagnet. And that comes into inductance, which I'm not really going to talk about here. And ask me about resistors a little bit later, because I'm going to go over this stuff first, but I'll get back to resistors. Please remind me about that later. Okay, so when I put voltage on here, the electromagnet has a north and a south pole. Here, let me put the phone down again. If this is a permanent magnet, and then here's the electromagnet, this has a north and south pole, and this has a north and south pole. when I energize the electromagnet, the north and south pole are going to, north and north are going to repel, so this is going to want to go flying. But the electromagnet is connected to this thin piece of plastic here, called a diaphragm on a speaker, and it goes as far as it can go really quickly as soon as that's energized. And then when I de-energize it, it pops back. And that will make a sound pressure wave go here, which hits my ear, which we'll perceive as a click. So since here is the LED, you can see it go click, 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 click. That's what we'll hear. It'll be really soft though, but let's see if it works. Can you hear that? No, yeah, the microphone on my phone is crummy. So anyways, that's what's happening. But I'm gonna make it go faster. This is not very interesting right now because the click rate, the frequency, the amount of hertz, the times per second, is too slow. Our human ears respond to between 20 hertz times per second and 20,000, 20 kilohertz. 20 hertz to 20,000. Right now, it's 5. That's way too low. So let me go back to the Blink program. You won't be able to see me do this, but I'm going to make both of the delays 10 and click the upload button. So right now it is, actually, here, I'll do that with my phone. Yeah, that's too hard to read. So anyways, it's doing that. I made both the delays 10, so this is going to be 50 hertz. Off for
Hey, Mitch,
10th of
I'm
a
just
second.
going to quickly stop you. I'm going to run out to the next workshop. We have 15 minutes left of this one.
Yeah, right, perfect. Okay, so now it's off for a 10th of a second, on for a 10th of a second. That makes 50 times a second overall, and I think you can hear this. Okay, so you can change that again. I'm going to change it again to be as fast as you can make it with the delay program, and that'll make it 500 hertz. Okay, so you can hear that. And I'm sorry it's taking so long between compile. It usually takes like a fraction of a second. An anti-static. You don't have to worry so much about anti-static with modern parts. It's still a consideration though, and if you're doing manufacturing, you definitely want to do that. Okay, it's uploading now, and there's 500 hertz, right? So that is playing a tone. And here, let me recompile to get a 10th of a second on off. So stick around just a little bit. I've just got a little bit more to go, and then we'll be ready. But imagine playing this tone for a while, another tone for a while, another tone. Then you can play a melody. And if you also add 12 buttons with 12 input pins, you can play a different tone depending on which button you push. And now you have a really simple music synthesizer, which is just a hack of Hello World. And yes, blue boxes can be done this way as well. So back in the day, but back in the day, microcontrollers were expensive. But blue boxes are pointless now because it's all digital. But blue boxes are still a cool thing. Okay, so I'm going to go back to the slides and show you the last bits. A solderless breadboard. Looks like I'm going to go over just a little bit. I'll try to make this fast. So a solderless breadboard is just very much like the holes on the side of the Arduino board, except that they don't connect to a microcontroller necessarily. There's no parts on here, but they're columns of 5. And they have labels for the human to read, like this hole here is hole 8B. And all 5 of these holes are connected to each other. So if I connect something into 8B and something into any of these other holes, like 8E, they're connected. They're not connected to any of the column 8 here. This break here gets in the way. But I can connect parts together. For instance, I can put this LED in here. And let me grab that LED. And it doesn't matter which holes, as long as they're left and right. So any hole up and down from one another when the board is oriented this way are connected together. Any of the 5 up and down from each other. Any hole left and right, not connected to each other. Okay, so right now I've got the LED in this picture, the short lead in column 7B, and the long lead in 6B. And I actually have that here on my table as well. Okay, now I want to connect this wire to the short lead. This is a black wire to the short lead. So what I'm going to do is connect it to any of these above or below 7B, the short lead. Okay, and here's a picture. And I'll do a similar thing to connect the red wire to the long lead. Okay, so now this red wire is the long lead. This black wire is the short lead. And if I connect this to ground and this to pin 13 on my Arduino, then this LED will blink. And I will do that here. Coolio. And I can also now add a resistor in the series. And all I need to do is pull out, which I'll do in my phone video up above, pull the black wire or the red wire out and put the resistor in between. And now the LED will blink, just not as brightly. So it's more dim. And if I put a bigger value resistor in there, it will blink even dimmer. If I put a smaller value of resistor, less resistance, the electrons flow quicker, more energy, brighter. Okay, so that is a simple circuit. Here's the schematic for it. Because drawing this, even if you're really good at the GIMP or Photoshop or whatever, it takes a long time and you have to be a good artist. Doing a schematic, I can do this super, super quick and I can do it on a napkin. It doesn't have to be neat and I can communicate to someone who doesn't even speak my same human languages about my project. With a schematic, I can communicate very easily to other people what my project is. And everything on the schematic diagram, every symbol is something in the real world. Like here. Everything here is a symbol on my schematic diagram. For instance, here is a black rectangle that says Arduino in it. It's not a trick question. What is this? It's the Arduino. And it's really common in a schematic, so it doesn't look as complicated, to only use the pins that you're using. So we've got power, which is my power supply. And we've got a resistor and a diode. Okay, so right now you don't know all these symbols, but you know this one. This is the Arduino. Here, oh, let me do this one first. This is marked GND. That's the GND hole that I hooked my power supply to, the black wire. And then a line on the schematic is a wire. So I have a wire going from the GND hole to this symbol. whatever that is, there's a wire going from the GND hole to this symbol. That same symbol's over here, so I have a wire going from the right side of this part to that same place. Here is another hole. It happens to be the digital 13 hole, pin 13 hole. And I've got a wire going to the right side of this part and the left side of this part, the left side of this part. And the right side of this part goes to the left side of this part with a wire. Okay, this symbol is ground. Wherever you see this, it just means connect the wire to the black of your power supply or a ground hole in your Arduino. And if you run out of ground holes in your Arduino, you can have a wire going from the ground to, let me show you the video on my phone again, to one of these columns. And now you've got 4 or 5 more ground holes that you can use. Because you can have lots and lots of wires. You have lots of wires. And yeah, so the right side of this part has a wire going to ground, the black of the power supply. And the left side of this goes to pin 13 hole. These two parts are connected with a wire. This is a resistor, the zigzag. And if you think of that like bumpy pavement, if you're an electron cruising along on the smooth wire, look on the screen now, smooth wire, you're cruising along on your little electron bicycle, everything is groovy, but suddenly you hit rough pavement, it slows you down. And that's what resistors do, it slows things down. And the value is written near it, in this case, 1K, 1000 ohms. This is the LED, which is a special diode. And diodes only let electrons go in one direction, which is why this looks like an arrow. And if you look, and a resistor, it doesn't matter which way you put it in. The diode, it does. So make sure that the arrow is pointing towards ground. And you can kind of think of this as it's an arrow pointing into a minus sign. See on the right here, there's a minus sign on its side. That's part of the symbol. That's the minus side. So that's the short lead going to ground. Okay, and then one other symbol on this is here, plus. And it gives the amount of voltage. So that's the red wire. All right. So let's look at the next schematic. That's the one we saw originally. And there's really not much more there than we've already covered. There's a transistor, which I have a picture of here, same picture as before, and it's not actually technically called input, ground, and output, ground, input, output. They're called CBE, collector base emitter. And yeah, so on the data sheet, you can look up, it tells you which pin is which with the picture. I did that for you, and most projects, many projects will. And this is the symbol for a transistor. And you have to know usually which is which, but I marked them here, C, B, and E. Here's 2 different resistors. Here's another resistor. Here is a switch. Remember a switch? Look at my fingers now on this video. Off, on, off, on, off. That's why the symbol for the switch looks like this, just like my fingers. Off, on, off. But the switch is quite often a little bit different. These little switches have 4 pins, and I showed down here how to actually wire it up. You want the terminals, if you have a 4-lead switch, even though there's the schematic only has left and right, you orient the switch so there are 2 leads up and 2 leads down, and then these 2 are both connected internal to the switch. It's kind of confusing, I know, but this is the left side. Either one of these is the left side. Either one of these is the right side. I also showed the color code of a couple of the resistors. I didn't show the color code for this one. But this is only to tell you if you're going to use European off-codes or North American off-codes. European works for Africa and Middle East, and North American works for Asia and the rest of the world. And if you leave this resistor out, then the program, our TV Be Gone sketch, knows to do only North American codes that work on most of the world. But Europe, Africa, and Middle East, you need that resistor in to do all of the off codes that work on those TVs. And that's really it. You know, here's the power supply with the schematic inside showing the schematic symbol for a battery and the switch on that. And that's really it. That's everything to make TV Be Gone work. And I gave you a lot of info. And unfortunately, I got to run now to my next workshop, so I'm not too late there. I got a minute. Feel free to ask me questions either on Matrix or my email, and I'll give you my email here. Typing it in. That's my email. I'll also put that in the shared notes area. There's my email in the shared notes too. So, yeah, sorry, I've got to run off, but I'm happy to answer questions after my next workshop, or if you're in the next workshop, you can ask me there too. Okay, so my next workshop is, let me put the, oops, that's the wrong page. Big blue button. I'll get the link for it. There we go. So workshops.hope.net/ oops, that's not it. That should be it. I hope I did that right. Oh, there's a space in it. That didn't work. Well, you can figure it out. I got to get going now. So thanks everyone for joining me. That was a lot of info, a lot of cool stuff. Feel free to play and email me, contact me anytime with any questions you have. I'm totally happy to help with your projects. As long as I'm alive and can use a keyboard or a phone or my mouth or whatever, I'm happy to help. So I'm off to my next workshop, the Arduino Touch, which will show people how to solder and how to make sound, really cool sound with, oh yeah, here's a bunch of those Arduino Touch synthesizers. So you can make lots of way cool noises. And here's some way nasty noises. Oops.
Hey, Mitch, don't forget, Mitch, don't forget to stop the recording.
Oh yeah, stop recording, and I'm off to my next workshop. Bye everyone for now.